Okay, let's get started. Hi guys, welcome to the stream. So in this session, we're going to do some mathematical statistics and exterior ballistics, like we always do every week, Saturday. So this is no exception. This used to be a series that takes place on a Sunday evening, but right now, in the near future at least, my Sunday evening is going to be occupied, so no content. Well, except for I was saying no content on Sunday except for the community post in the morning, usually in the form of quizzes. So anyway, so here in what are we doing this week? So here we're going to cover the notion of hang on a second. Yeah, more likelihood inference actually. So we've been studying in some quite detail actually with quite studying with some quite detail with quite some detail about the notion of sufficient statistics. My bad. I just took a nap before I started the stream, so this way I have energy during this live. So apologize for my incoherent speech. Okay, so here we are in this section, maximum likelihood estimation, 6.2. Okay, so of course we will. I hope we can go over the main text quickly and do some exercises. In section 6.1, we introduce the likelihood function, L. So L. Recall L, the likelihood function, is defined as such. So L is a function of theta for a given sample. S is a sample, and L theta given S is numerically the same as Fs given theta. So suppose that theta is the true parameter, then f of s given theta is the density or the PMF, depending on whether the model is discrete or continuous, of the model. So numerically they are the same. However, the perspective is changed. In the likelihood function, s is treated as a fixed parameter, whereas theta is the actual variable. And in fact, the absolute value of L does not matter. Okay, if two likelihood functions differ only by a multiplicative constant, then they are considered equivalent. Okay, and this is not true, of course, for probability density, because probability density needs to have this property of normalization. You integrate the probability density, you should always get 1. Otherwise, it fails to be a probability density. In the likelihood function, we simply don't care. What we care about is the relative magnitude of the likelihood function. So what likelihood function really does is it imposes a ranking system on the set of parameters, on the set of possible values of parameters, and higher relative values of L indicates the relative preferability of the parameter. The bigger the likelihood, we consider it to be more powerful when it comes to explaining the sample S. Okay, so that was a brief review of what likelihood function is and why it is not a probability. So that likelihood function is a basis for making inferences about the unknown true value theta. Okay, so theta is the true value. And here, by the way, here we're using the notation big omega for the sample space. This is rather unusual, actually. I mean, of course, the notation it does not matter. You can use whichever letter for whichever set. But here, big omega stands for the parameter space. Okay, which is a little bit unusual. I'm surprised that it is true in this way. So typically in mathematical statistics and probability theory textbooks, big omega is referred for sample space. That is, big omega is supposed to be is by convention, okay, supposed to be this the set of S, whereas the parameter space is usually denoted as big theta. So big theta and big theta is, it looks like a helicopter a helicopter pad, launch pad. Okay, so that was the parameter space in most literature. Okay, but here we're using big omega as the parameter space. Just not get confused about that. Okay, so pay attention to the notation convention in this book, even though I think it is rather unusual. Anyway, we now begin to consider the specific type of inferences discussed in 5.5.3. Okay, let's do a quick review of what's covered there. We should have seen this already, because chapter 5 was most of chapter 5 was discussed several weeks earlier, and start with that estimation. So let's go back to 5.5.3 and see what kind of inferences was discussed over there. 5.5.3, did we cover that? Actually, we skipped 5.5.3. Oh, my bad. Type of inferences. We might have to do a quick overview of that, because we still want to come back to 6.2. And before I do that, let's read a chat message. Thank you very much, Anu. Hello, sir. I'm amazed how you have mastered so many different. Well, I wouldn't call myself a master. It's just I've taken many courses, and now I wish to come back to them and learn them in a more, so to say, in a way that it enforces fundamental understanding rather than problem solving. I mean, problem solving is important. I'm trying to say is root memorization. Okay, I'll be honest. When I studied these things in the university, many of the details, many of subtleties were I glossed over. I was just happy about solving the problem sets, the exam questions, but there's a lot of underlying subtleties that usually not emphasized in standardized tests, and I wanted to master the intricacies of them. So I'm not a master, but thank you very much. And how can you share some tips not to get concept mixed and retain clarity? I guess the most important thing is, first of all, try not to make mistakes. Try not to avoid mistake. Okay, make as many mistakes, because right now, you say, as I say, I'm not in university anymore, right? So I have all the incentives to not hide my mistakes, and instead just say, okay, I understand this, I don't understand that. So be honest. Okay, it sounds a little bit simple, but really to maintain clarity, and not confuse yourself. First, you have to be honest with yourself, what you really understood, and what was accepted as given information, without actually questioning what it was really about. So I think that's the first one. And second is what I'm trying to do here. Okay, try to explain the concept yourself. Like, see if you can make a logical explanation in a way that is almost like you can rediscover the method on your own, like as if it is independently discovered. So try to make that sort of explanation. I mean, right now I'm doing it live to a YouTube audience, but it doesn't matter, right? I can still do this to myself. If I just turn off this live and just try to convince myself whether a topic is really understood. So if that is possible, so if an explanation as if I was able to rediscover it myself is possible, chances are I have some real understanding. Okay, so that's the idea. Okay. As they say, teaching is the best way to learn, right? So it's kind of similar to that idea. Okay, so coming back to 5.5.3, this section is more this less messy. Okay, it's less messy, but we still wish to understand what we mean by inferences and what types of inferences we want to do. It says, certainly, quoting descriptive statistics and plotting the data are methods used by a statistician to try to learn something about the underlying population distribution. There are difficulties with this approach, however. Okay, as we have just chosen this method based on intuition. Okay, often it is not clear which descriptive statistics we should use. Furthermore, these data summaries make no use of the information we have about the true populational distribution as expressed by the statistical model. Namely, fx belongs to the collection of functions f theta, theta in big omega. Okay, so taking account of this information leads us to develop a theory of statistical inference, i.e., to specify how we should combine the model information together with the data to make inferences about population quantities. We will do this in chapter 6, 7, and 8, which actually is the focus of this series on mathematical statistics, introduction to mathematical statistics. But first, we discuss the type of inferences that are commonly used in applications. Okay, type of inferences. So that's the first thing we wanted to clarify. Okay, so let me just write that in my notes. 5.5.3, and this is from Evans and Rosenthal. Evans and Rosenthal, fantastic textbook, completely for free. So everyone who asks for a recommendation of basic statistics, get my recommendation for this one. Rosenthal is completely free, and it has a solution manual also for free. What else could you ask for, right? Evans and Rosenthal. Professor Evans is a big name in the statistics community. And so is Rosenthal, actually. So Rosenthal has two more fantastic books on stochastic process as well as measures theoretic probability. Okay, great. Furthermore, these data summaries make no use of the information we have about the true populational distribution as expressed by the statistical model, namely fx in f theta, theta in big omega. Okay, actually we read this already. Let's continue with the next paragraph. Actually, coming back to chat, says, sir, I also wanted to understand what is your views on fundamentals. When should we stop our brain and say it's okay? Basically, my brain always tries to overanalyze, and I don't know where to stop. Okay, that's a good question. Should we go up to axioms, and if yes, should we do that for all problems and just do one and accept the facts? Okay, so good question. This is very practical. Thank you very much for posing that question. So, I mean, when it comes to fundamentals, actually, there is this problem of the right amount of detail, right? The right amount of detail, or the workable amount of detail, a workable amount of detail. So, I think when it comes to the fundamentals, so what I do is I follow the mainstream community. I know it sounds very conformative, you know. So I think it is a time management thing, right? Just what time you should spend on, right? Should you spend more time on digging the foundations, or should you get a passing familiarity and move forward, and perhaps when things are appropriate, you come back to that. Okay, so so I pretty much, I think I gave an example on Friday when I was on the complex variable Russian stream, okay, Russian style complex variable stream. I said, okay, think about the sine function, right? Sine function, cosine function. You first learn it in a right triangle, and it is good enough application. So it's good enough for many applications of the trig function. So this is sine, this is cosine, and this is 1. Right? You first learn it in a right triangle, and then you learn it in a coordinate system. So now sine and cosine can take both positive and negative values. So this is a workable definition that you can use for most applications in geometry, in mechanics, physics, all kinds of things. Right? So this is a workable definition. And at some point you will learn, sine theta, cosine theta is actually defined in terms of either power series or complex numbers. This is not really a definition of sine theta, because using this definition is still quite hard to calculate, say, cosine of 1. What is cosine of 1 based on this definition? So first of all, what is the angle of 1? It's quite hard to calculate sine and cosine based on this definition, right? So that's the thing I was talking about. So when you reach a stage where the current definition feels insufficient, you can dig deeper into the foundation. I mean, as applied mathematician, I mean, that's just my perspective. As applied mathematician, I don't dig up foundation for its own sake, but rather I do so on a need-to-know basis. So if the geometric, if definition, quote unquote, or more like description of the sine and cosine function is good enough for my application, I live with that. Okay, totally. And when saying, say, if I wanted to really say without a reference of diagram and say what cosine of 1 is, I realize the inadequacy of my knowledge, and I say, oh, I have to go deeper and say, define the cosine and sine function in terms of complex variables. That is, cosine of theta equals e to the I theta plus e to the I minus I theta over 2, or it's the sum of, it's the sum of the theta to the 2n over 2n factorial times minus 1 to the n, and from 0 to infinity, right? Both are okay. So the thing is, you have these people in real life and online, telling you that, oh, you don't really understand trig function unless you define trig function in one of these two ways. That's nonsense. That's just pure nonsense and snobbery, right? So the high school definition of sine and cosine are adequate for most applications, right? And there's nothing wrong with that. And if you reach a certain point that the so to say the geometry independent definition of sine and cosine is called for, well, you learn that. It's totally okay to stick with one workable definition and master it, and come back and learn a new perspective. Right? So, this is just I hope I answered that question in a more just, I mean, it's, of course, their personal opinion being added to it. Okay, I do admit that, but that's my approach. Yeah. So basically, we should do enough, but not necessarily absolute everything. Exactly. Time. This is time management. This is a time management problem. Totally. Say if your primary objective is to apply trig functions in geometry, how would this help you? How would these two definitions help you? Right. So, logically speaking, you really should start from a logical standpoint. Okay, you should start from defining the trig function using complex variables or power series, and then say, okay, I'm going to model geometry based on this function, instead of taking things, saying things like this is the definition of cosine. Right? This is a logical approach. But logical approach is rarely the most pedagogically sound approach. Right? So imagine trying to teach high school students who never seen the triangle version of sine and cosine and telling them this is the definition of cosine. Do you think they will find this helpful, or just pure torture? Right? Yeah, exactly. So yeah, I'm going to move on. In section 5.2, we actually covered this section. We discussed three types of inferences in the context of a known probability model as specified by some density or probability function f. We noted that we might want to do any of the following concerning an unobserved response value s. Okay, so we might do any of the following concerning an unobserved response value of s. Okay, so that's something that we emphasize here. So the response currently is unobserved. So we want to predict an unknown response value s via a prediction. Right, so the prediction is something that you can calculate based on the existing sample, and it is supposed to in some way approximate the unknown value. right? So it's like based on the current stock chart, you want to predict the value for tomorrow's value. That's a prediction problem. Second, construct a subset C of the sample space S that has a high probability, okay, of containing an unknown response. So this is part 2 is really an extension of part 1. So part 1 is only to provide a numerical prediction, just one number. And part 2 is instead of giving just one number prediction, you're giving a subset and say it is highly likely that the new or the future response would occur in that set. So in elementary statistics, we typically call the subset C a prediction interval. It's typically an interval, okay? So that's the difference between 1 and 2. So the prediction in part 1 is just a number. The prediction in part 2 is an interval or a subset. Okay. So 3, assess whether or not S naught, okay, S naught in S is a plausible value from the probability distribution specified by F. So S naught is meant to be a given value. Say if someone says, right, tomorrow the stock price would be I don't know, $190. SP 500 would be $190. Do you think that's likely? And on what basis do you answer that question, right? So this is a hypothesis, basically. 3 is a hypothesis testing question. Is a plausible value. Of course, you have to specify, okay, what do we mean by a plausible value? How plausible is it, right? So, so this is 1, 2, 3 are all about predictions. We refer 1, 2, 3 as inferences about the unobserved S. The inference of this type is different from inference over the unknown parameter theta. And there's a nice correspondence between 1, 2, and 3, part 1, 2, and 3, and inferences about theta. So in inferences about theta, we also have a point estimation. So in the theta department, okay, so part 1 would be a estimator, just a point estimator for the unknown parameter. Say we use the average to estimate the mean of the Gaussian distribution, like that. Just one number. Use one number that can be calculated based on the sample to estimate the true parameter. And second is the problem of finding confidence region. So we wish to construct a region, confidence interval for the 1D case, and confidence region for multi-dimensional parameters. So confidence region is a subset in the parameter space that we consider to have high likelihood, high probability of containing the true parameter. The technical definition of a confidence region is rather complicated, and we're not going to go into there now. But it's still, the idea is part 1 is just a single number as an estimate. Part 2 gives a range for the estimate. And part 3 is hypothesis testing whether a hypothesized value of the parameter, say theta naught, is true, is plausible. This is a hypothesis. H naught says theta naught is plausible. For example, in pharmaceutical research, the most common H naught, the null hypothesis, is that the new drug is no different from the old drug. Okay, no improvement. That's the null hypothesis you wish to reject, right? If you're developing a new drug, right? So there's a nice correspondence between inferences about parameter and inferences about the unobserved observation. Okay, in principle, 1, 2, 3 here, inferences about the unobserved response is harder. It's harder than inferences over theta. Okay, because as an unobserved response itself carries randomness, whereas theta is well, at least in our setup, theta is treated as a fixed number. So generally speaking, inferences about theta is can be infinitely accurate if you have infinite sample size. Well, theoretically speaking, in practice, that's usually actually not the case. But theoretically speaking, if you have infinitely many number of observation, the study of theta can be as good as you like. However, that is not true for inferences about unobserved S, because S, if you learn theta perfectly, S still has its intrinsic randomness in it. Right? There is this hard limit when it comes to prediction. So that's why prediction is hard. I actually made a video a while ago, a month or 2 months ago, called Confidence versus Prediction and the geometry for that. Okay. So these examples of 5.2 shows that they're intuitively reasonable concepts. Okay. In application, we do not know F. We only know that F belongs to a certain family. Actually, you don't even know that. You don't even know F belongs to a certain family. That's your hypothesis, sometimes often made to make analysis trackable. Right? Let's say we assume that the response follows a Gaussian distribution, right? And like God didn't tell you that, but you made that assumption. You assume that your quantity of interest follows a Gaussian distribution. Sometimes it's not what we know, it's something that you assume to make analysis trackable, especially in multivariate analysis. In multivariate analysis, we make even more liberal assumption that the multivariate data set is Gaussian distribution, which is perhaps less likely to be true compared to the univariate case, but we still do that simply to make analysis trackable. Right? At least in the classical multivariate analysis, at least in classical multivariate analysis is concerned, so we make frequent use of multivariate Gaussian distribution as the quote-unquote model. Right? In reality, whether or not that is true, it has to be taken with a heavy grain of salt and needs extensive testing for that hypothesis. Okay, just wanted to mention, we know only that is sometimes not achievable. And we observe the data S. We are uncertain about which candidate F theta is correct. Okay, we're uncertain. Yeah, certainly that's very true. Or equivalently, which of the possible values of theta is correct. Yeah. So here we assume there is this one-to-one correspondence between the parameter and the correct probability measure. So if two theta values are different, they correspond to two different probability distributions. Otherwise, you cannot identify the distribution. Okay, so this is just not how we parameterize our model. Okay, so there's that. Let me just briefly put on some notes here. So types of inference. Types of inference. You can do this for, as I said, for both theta and S, where theta is the true parameter and S is a future response or unobserved response. Okay, it can be, say, a piece of missing data, in which case that won't be a future response, it was simply an unobserved response. Okay, so inference for theta is typically called estimation. Actually here, inference about theta is called estimation, and inference for, actually, you know what? Let me reorganize the notes this way. For theta is called the problem of prediction. No, that's nonsense. Inference about theta is the problem of estimation, whereas inference about unobserved response is called prediction. Because these are fundamental definitions. Okay, so there's that. And in each case, you can give a point estimate, or you can give a set estimate, or you can set up a hypothesis testing problem. Okay, so this is estimation. This is prediction. I'll come back to chat in a second. Okay, and in three common questions. So three common techniques. Okay. One is point estimate. Is point is a point. I mean, I hate to use the word estimate because it also covers the point prediction. Okay. Yeah, let's just say point. Okay, point. And second is subset. And the third is hypothesis testing. Okay. Anyway, I'll come back to chat. Chat says, but the problem here is something else. Say that we use these trig functions in calculus and we should think about trig inside them or accept their properties. Sorry for asking irrelevant question. It's not irrelevant. Well, I was using, for people new to the stream, I was using the trig function as an example of the right amount of detail, okay, or level of fundamentals we should master before we move on. Okay, so when it comes to properties of trig, right, that's typically considered as pre-calculus. Properties of trig identities, double angle formulas, and whatnot. So let's say you're in the level of calculus, right? You're learning differentiation and integration. If you don't have those preparations, it will be very difficult for you to do, say, trig substitution. And learning the properties of trig function at a pre-calc level, right? Once again, without the rigorous definitions, is totally fine. Right. So I think for the purpose of calculus, and once again, these sort of prerequisite issues always a bit tricky. It's good to have experts' opinion. Right? I mean, we know learning math is mostly about yourself, is mostly, so to say, one's own effort, but you do need sometimes expert commentary. So not always like hold your hand all the time, but just a little bit of guidance. So I think if you want to say study calculus, and trig functions should be mastered to a level that you're able to derive trig identities based on the geometric definition alone. So you should be able to work out through, say, the definition, so not definition, but the workout, say, the formula for sine of theta plus phi on your own based on the geometric definition. So there's that. That's just, I think that's my standard. That would be my standard, because a lot of the trig identities are interconnected. So if you know the sum formula, you immediately know the double angle formula. That's an obvious example. A lot of the trig identities are interconnected, and if you just memorize them as facts one at a time, it will be a painful experience. It's just really an inefficient way to study. So yeah, spend some time on pre-calc, revisit the properties of trig before doing calculus. So it will save you time in the long run. Okay, question. So like, do we break the topic and go inside the building blocks? Yes, yeah. If you, let's say, if you in calculus and say, oh, I don't know trig function very well, right? Make that honest assessment. Once you make that honest assessment, based on your, say, your inability to do trig substitution, close the calculus book, come back to Calc 1, do the derivations of trig, and then come back, to calculus again. This will save you time. Yeah, because you don't want the difficulty of, say, of pre-calc to mingle with the difficulty of calculus itself. So the problem is, the problem for a self-learner is to identify exactly where you struggled. Okay, is to identify where you struggle. That's so important, because this is the most efficient method to improve. Because once you located the exact point where you struggle, you certainly have the precise information to move forward. Okay, what we wanted to avoid is there's this giant big blob of confusion. Wow, calculus is so hard. But when, say, if you ask yourself the second question, why is calculus hard? I don't know, man. It's just it's just such a big mess, and it's above my head. The calculus, the integral table, it has so many formulas. This is self-defeating. Instead, do what I just said. You try to find exactly where you struggled. If you say you can't do integration of trig and you realize, oh, it's actually because I don't have good understanding about some of these identities. Say I don't know how the trig substitution identity is used. Say, let's say you can't say yeah. I'm just giving. I don't want to spend more time on this, but basically, if you see in the trig substitution section that there are certain identities you cannot derive yourself, go back to trig. Okay, question. So here I'm curious about your thought about the order of math one should go through prior to learning math or statistical modeling. Learning machine learning, well, just multivariable calculus and linear algebra. And actually, in a reverse order, linear algebra first and multivariable calculus second. You can sort of get away with not knowing integrals in multivariable calculus. Actually, you know what? Let me just use this set of notes as an example. Paul's online notes. Paul's online notes math. There you go. Here. This is an excellent source, free source about calculus. So in Calc 3, this is a typical Calc 3 curriculum. The first part is about multivariable differentiation, partial derivatives in a nutshell. And the second half would be multivariable integration, multiple integrals, including vector calculus. Okay, so if you want to study math for the purpose of machine learning, you want to do linear algebra first at the level of Gilbert Strang's linear algebra text. Go to MIT OCW, linear algebra. Okay, so this one by Gilbert Strang, world famous class. You see, you have video lectures as well. Don't watch my video if you want to learn linear algebra. Watch Gilbert Strang's. Okay, so his lecture is unmatched. It's unmatched by, I would say, just anyone in the world. Like if you're a complete beginner to linear algebra, there's no better videos than his. Forget about everything else. Okay, just follow this and do the exercises. There's even solutions. What else could you ask for, right? Well, you do need to have his book, Strang Introduction to Linear Algebra. Get that book and do the problems. There are solutions, step by step. Okay, and then do calculus 1, 2, 3. Do calculus 1, 2, 3. Yeah, and you can get away with not knowing multiple integrals until you reach statistics. So let's say if you're studying machine learning algorithm, if you understand linear algebra, and you understand partial derivative, then you have enough math to build your own neural network. Okay? Sounds a little bit crazy, right? But yes, I'm not joking. If you know linear algebra and you know partial derivatives, you have enough math to build your own neural network. However, if you want to approach statistics and machine learning with a probabilistic perspective. So you want to study, like what we're doing here, mathematical statistics, then you cannot skip multiple integrals because things like expectation variances are integrals. So you need to study those to get a basic understanding of probability, and then you can study machine learning from a probabilistic point of view. Probability, and so that's the traditional stats, right? That kind of stuff. So basically, to learn ML, calculus, and linear algebra all the way. Okay, and from there you can choose to specialize. So you want to learn more about optimization. So you want to go, if you want to do more stats, and because at that point you are no longer a complete beginner and you have a sense of direction, and you no longer need my advice. Okay, so yeah, so you were thinking linear algebra, calculus, statistics, totally legit. Okay, and I was just saying for a lot of machine learning application, you can get away with not knowing multiple integrals. Joa, thank you very much for being a channel member. Joa asks, what are your thoughts of using empirical distribution when the data doesn't fit any standard theoretical distribution? That's a very good question. So of course you should prioritize evidence and not theory. So when, say, empirical distribution doesn't fit any standard distribution, this creates difficulty in trackability. Right? This creates difficulty in trackability. So you have an empirical distribution, it does not look like any standard distribution. Say, for example, it really depends, right? It really depends on what kind of deviation you're talking about. So let's say if you see your distribution is multimodal. Of course, there's no standard, quote-unquote, standard statistical model that corresponds to this. What do you do? Well, you can just work with the empirical distribution itself. Yeah, just take the empirical distribution as given, and then go full numerical, full simulation-based study. You're not going to make any parametric assumption. Okay, you just stick to the empirical distribution, because this is now a valid distribution. It is not standard, but it cannot be described by any sort of standard parametric model. You can say calculate. You can do inferences, okay, based on drawing fake data, okay, synthesized data, that is new Monte Carlo simulation from this distribution, and then proceed from there. Go full computational. That's one possibility. Or you can think of how to combine classical models in an ingenious way to replicate the behavior of your empirical distribution. So, okay, for example, here you have a multimodal data set. Can we consider this as a mixture of Gaussian? So each mode corresponds to one Gaussian, right? And then you just take the weighted average of them. So this way now you can parameterize the model. Of course, estimation will be harder and require special techniques. A mixture of Gaussian, for example, would need ENM algorithm, that is expectation maximization algorithm, to find the maximum likelihood estimator. Yeah, so it really is up to you. I mean, you have this arsenal of tools, and it's without further details, it's hard to argue which method is more valid. Okay, so it really boils down to what kind of deviation you're dealing with, and whether you wish to go full numerical, or you want to somehow combine classical models in a creative way to address the deviation you observe. But regardless, reality comes first, and mathematics or models are secondary. Okay, nature does not need to agree with your fancy math. Okay, okay. So let's delete that. Thank you, Andre, for the question. Matrix analysis is the best book to understand linear algebra in real depth. Well, yeah, that's certainly, I mean, one particular aspect of linear algebra, that's matrix analysis. Although matrix analysis, I would say, is perhaps only approachable if you have a basic working knowledge with, say, strings linear algebra, because matrix analysis is usually quite specialized. So in matrix analysis, you're dealing with special kinds of matrices. So for example, matrices with all positive entries. That's a common topic, right? Matrices of all positive entries, because often, say, if you study Markov chain, the entries are all probabilities which are non-negative, and even better, each row sums to 1. So it's a very special structure. These kind of matrices aren't dealt with specifically in linear algebra, but to study them, you need a passing familiarity with basic linear algebra. Yeah, matrix analysis is about the study of specific kinds of matrices and computational techniques. So, yeah, I think I'm all caught up with chat. Let's see what's next here. Okay. As mentioned in section 5.5.1, our primary goal may be to determine not the true f theta, yes, but some characteristic of the true distribution, such as mean, median, or the values of the true distribution function at a specific value. Yeah, that's certainly correct, because sometimes you don't need a full distribution, you just need certain characteristics of it. Yeah, so we denote this characteristic of interest by psi of theta. So psi of theta is a function of theta. So psi takes a parameter and returns some numerical number, some numerical value. So that's the quantity of interest, characteristic of interest. For example, when the characteristic of interest is the mean of the true distribution, what you really care about is this integral, and not the full function f theta. Alternatively, we might be interested in psi theta equals big F inverse theta at 0.5. So that's the median. Right, so that's the median of the distribution of a random variable with distribution function given by f theta. Different values of theta lead to possibly different values of the characteristic. Yeah, no doubt. After observing the data S, we want to make inferences about what the correct value is. Okay, cool. The correct value of psi theta. Okay, we consider the 3 types of inferences for psi theta. Okay, and here you have the 3 types which correspond to parts 1, 2, and 3 I just described. Okay, this is slightly more general, because here I just wrote theta. You can estimate theta, confidence region, hypothesis testing, but here we're actually doing it for a function of theta. Doesn't have to be theta itself, okay? It can be a function of theta. Choose the TS of psi theta, referred to as the problem of estimation. Construct a subset CS of the set of possible values of psi theta that we believe contains a true value, referred to as the problem of credible region or confidence region. So the special terminology, okay? Credible region is the correct terminology in Bayesian statistics, whereas confidence region is the terminology in frequentist statistics. Okay, so we're going to do frequentist first and then Bayesian second, because you can't really understand what Bayesian is about unless you already understand the frequentist perspective. Bayesianism arises as a reaction and in their opinion, in a Bayesian point of view, the completion of the frequentist project. Okay, so that's why there's different terminologies here. So let me just change my notes a little bit. Types of inference for psi of theta. Psi of theta is not necessarily a true parameter in itself, right? It would be the true characteristic of the distribution, or should we say characteristic of the true distribution. Let me rephrase that. Not necessarily as a true parameter, but rather the characteristics of the true distribution. Certain characteristic of the true distribution. So that's the problem of estimation. Okay. And maximum likelihood estimation, of course, is an estimation technique. Okay, and whether or not psi naught is plausible for psi theta after having observed S, referred to as the problem of hypothesis assessment or hypothesis testing. Okay, so estimate credible or confidence regions and hypothesis assessment are examples of types of inferences, types of inference. Okay, in particular, we want to construct estimate TS, right? Construct estimate TS of psi of theta, or construct credible or confidence region CS for psi of S, and assess the plausibility of a hypothesized value psi naught for psi of theta. The problem of statistical inference entails determining how we should combine the information in the model and the data to carry out these inferences. Okay, I think this is an important comment. Let me just put that down. Okay, you can't just looking at the data alone, and although sometimes you have to. Sometimes you have to, and perhaps it is also a good idea to look at the data first without any model assumptions, because model is fundamentally a subjective thing. The act of modeling is fundamentally a subjective thing. So, well, heck, what you choose to measure is already fundamentally a subjective thing. The data in themselves might be undisputed, might be universal, but what you choose to measure is a subjective thing. Well, the aspect of reality you choose to focus and to choose to ignore, that's totally subjective. So, modeling is an extra layer of subjectivity. So, what we're doing here is to combine the model information, combine your assumption as well as data together to get the information about whether it's a true characteristic or it's an observed response, if that makes sense. Okay, so let me just have a sip of water and I'll be right back. Okay. So, problem of stat inference. Okay, so this is a really high-level knowledge, high-level view. Okay, what does stat inference is? Stat inference is about how to combine information in model and data. Okay, so that's the problem of statistical inference. Okay, so let's see. These are just examples that comes next. Okay, so these are examples, histograms. Okay, so I think we're ready to go back to section 6.2. All right, yeah, 6.2. Yes. Here, remember, the reason we went back to 5.53 is because here in 6.2 it mentions specific types of inferences discussed in 5.3. Three types: point estimate, point estimate / point prediction, interval estimate / interval prediction, as well as hypothesis testing. Okay, cool, let's go. When we are interested in the point estimate, the first type, then the value theta hat of S that maximizes L is a sensible choice, right? So we've been hammering the point that the electrical function itself imposes a ranking system on the set of parameter, on the set of possible values of parameter. So it is natural to see what is the parameter that maximizes preferability. Right. So it is in this sense that statistical inference becomes a sub-branch of optimization. Right. At the end of the day, like if you wish to come up with an estimate, let's say in machine learning you want to train a model, quote unquote train a model. Right. mathematically speaking, is just maximize or minimize a cost function. Typically, you minimize a cost function, right? Or here, maximize likelihood. So mathematically speaking, training a model is an optimization problem. Okay, this is a sensible choice, as this value is best supported by the data. So you want theta hat to have this property. So theta hat, the value of L at theta hat given S is greater or equal to all possible values of L for any theta in the set big omega. So let's draw a picture. So this is the function L of theta given S, and this is the theta value, assuming that theta is a scalar. So let's say this is your likelihood function, and the point at maximize the likelihood is called theta hat. This is MLE, maximum likelihood estimator. So we have this definition. We call theta hat, which is a map from S. S is sample space. Okay. S is a sample space to big omega, satisfying this inequality. For every theta in big omega, a maximum likelihood estimator, or MLE for short. Okay, so there's a little bit of a terminology subtlety here. Okay, so you see the function itself is called an estimator, and the value of the function is called an estimate. An estimate. So yeah, this is not splitting hair, because the likelihood function, no, not the likelihood, the maximum likelihood estimator is a random variable. It's a random variable because later on we would like to randomize the sample and determine the distribution of theta hat. Right, this is one common type of study, and in fact you can argue over 80% of mathematical statistics is to calculate all sorts of sample statistics, to calculate all sorts of sampling distribution of statistics. That is to say, you use a transformation of the random variable, and you want to see how it is distributed. Right, so that's a huge part, if not the majority of work for mathematical statistics, is to study the transformation of random variable. Okay. So yeah, that's notational and terminological differences. Okay, a maximum likelihood function, a maximum likelihood estimator refers to the function itself. Maximum likelihood estimate refers to the function value. Suppose that little s is already observed. Okay. So there's no randomness in there. And you can calculate the value of theta hat of s, and that's called a maximum likelihood estimate. Okay. Let's put that definition down. Definition 6.2.1. Okay, so given, let's say, model. So f theta, where theta is in the parameter space omega. Okay, given this model, we say theta hat is s to omega. Here S is the sample space. So if that's true, hang on a second. Yeah, if this is the MLE is A actually. Let's not use the, because we don't know whether the MLE is unique. Is a maximum likelihood estimator. Currently still the most popular paradigm for estimation, MLE, because of its desirable properties. I believe we will see some of them in chapter 8. Maximum likelihood estimator, MLE. We say this is an MLE if the inequality holds true. F of theta hat of S Okay, given S is greater or equal to L of theta given S for all theta in big omega. And I believe you need to add for all possible sample as well. So this function has this property for all possible sample point S as well. So this is not explicitly mentioned in the text, but I believe this should be added. Otherwise, this S is a free variable. You have to quantify over them. Right? So going back to my series on proof writing, right? If a statement, if an inequality has a free variable in it, it is not a statement. It's like if you say m plus 1 greater than 3, that's not a valid statement in the sense that it does not have a truth value, because the truth value of this statement depends on the value of n. But instead you say, okay, for all n in big N, n plus 1 equals greater than 3. And that's a valid statement even though it is false. So here I think we should quantify over S, okay, just to be ultra clear. Okay, here it is not mentioned in the textbook, but let's emphasize that. See, I only mentioned for every theta in omega, but I believe this also needs to be true for all S in the sample space. Okay, so yeah, that's the maximum likelihood estimator. Let me highlight that. Estimator. Okay, and the value of the function for a given S, the value theta hat of little s is called a maximum likelihood estimate for a given theta. Not given theta, but given S. So this is called a maximum likelihood estimate. Okay, so because the estimator is a random variable, I'm just gonna emphasize that here. This is a random variable, and its estimate is just a number. This is a number. Estimator is a random variable. All right. So yeah, there you go, and or MLE for short. Okay. So in this definition, it raises a few questions. So first of all, how do we know the function can be maximized? How do we know if the maximum actually exists, right? There's no a priori reason that a function has a max value. That's for one. And second, is the maximizer unique? And the answer to both of these questions are negative in general. Okay. However, for most textbook examples, you will find quote-unquote well-behaved model. The MLE exists and is unique. But in general, there's no guarantee for that. Right. A great challenge in high-dimensional machine learning, or let's just say fitting high-dimensional models in general. Right. By high-dimensional model, I mean the model is parameterized by a large number of parameters. The cost function is typically, it is unclear that whether the cost function has a minimum or a maximum, and how to extremize it. What would be the suitable algorithm to apply? Okay, it's not like optimization is a very well understood problem. Okay, there's a lot of progresses have been made, but optimization in general is still very difficult. So we're just giving out this condition, and without going into the detail of whether max or min exist and etc. Okay, that's very tricky. Okay, just wanted to point out the difficulty up front. So in general, I mean, so that's why in general MLE is difficult to calculate. MLE is in textbook examples. I mean, for learning the main idea, the calculation tend to be rather straightforward, if tedious. But in general, finding the max or min value of a function is not a trivial problem. All right, let's continue. Notice that if we use C times L as the likelihood function for fixed C greater than 0, then theta hat of S is also an MLE. Right? If you just say multiply your likelihood function by a fixed constant, this inequality is still true. So yeah, it does not change the MLE. Because as we mentioned, if two likelihood function is different by a multiplicative constant, then they're considered equivalent. So of course, equivalent likelihood functions give the same MLE. In fact, they give the same inference overall. Okay, so we can use any version of the likelihood to calculate MLE, and usually you pick the simplest version. You ignore multiplicative constant that has nothing to do with the variable theta, sorry, not the parameter theta, and you do the algebra with that. Okay, so now let's take a look at a simple example. This is perhaps the simplest possible example imaginable because the parameter space is just two values. There's only two competing values for the true parameter. Okay, and don't overlook this as some kind of unrealistic example. This happens all the time. This happens all the time in practice. Can you think of an example where the parameter space is binary? Well, think of a justice system. Think of a justice or the criminal investigation. 1 means the suspect is guilty in the sense that he or she actually committed the crime, and 2 is innocent. That's binary. So suppose f of s is a measurement of the suspect, a measurement of the suspect. Yeah. So f of s is some sort of measurement of the suspect. So it can be, say, his lifestyle, his change in the financial situation, or it can be psychological profile, something like that. Right. So, yeah, if say the distribution, we hypothesize, okay, we hypothesize that the distribution of that particular characteristic, say financial situation, psychological profile, etc., can be described as a distribution. So 1 would be the distribution when the suspect is guilty. F2 would be the distribution when the suspect is innocent. So something like that. So this can happen in real life. It's not just a toy model. Or in physics, in science in general, you have competing theories. Right? Let's call 1 the established theory and 2 is the alternative. Right? So you can hypothesize, let's say, under the established theory, what would be the distribution of a quantity of interest? That's F1. And 2 would be the distribution of the quantity of interest under the assumption that the alternative theory is true. And you just compare them. All right, so this can totally happen in real life, I'm just saying. Suppose the sample space is 1, 2, 3, and the parameter space is 1, 2, and the model is given by the following table. Okay, so very straightforward. Okay, and in fact, when we deal with infinitely many alternatives, we can still mentally construct this table to help us visualize what is actually being compared. So you're comparing F1 and F2 here. Okay. When you have multiple models, you're comparing, say, one row against the rest. Further, suppose we observe s equals 1. So s equals 1 is observed. So which would be the parameter value that support this particular observation more? Well, obviously it should be 1, because the probability of s equals 1 when 1 is the true parameter is 0.3. Whereas the probability of s equals 1 under 2 being the true parameter is 0.1. So the parameter 1 maximizes the likelihood. Okay, so let's see what the textbook says. So for example, we could be presented with one of the two bowls of chips, right, containing 3 portions of chips labeled 1, 2, and 3. Okay, so this is a fun example. So say 1 is say Dorito. Okay, and 2 is say Pringles. Okay, and 3 is what? Cheetos. Okay, so you got three types of snacks, and they all mixed up in a chip bowl. Okay, so the first model says 30% is Dorito, 40% is Pringles, and 30% is Cheeto. Whereas second model says 10% is Dorito, 70% Pringles, and 20% Cheetos. You got to choose one model between the two. So what do? You just pick one chip from the bowl. I mean, the bowl is one. The theory is competing. The reality is fixed. Okay, you pick one chip, and you realize, oh, that's a Dorito. Okay, so you want to now say something about the underlying distribution, right? So what do you say? In this case, a MLE given by theta 1 hat is 1. Right? So theta 1 hat is 1. Since 0.3 equals L of 1 given 1, so the first one refers to the parameter equals 1. The second one refers to the observation s equals 1. Okay, and which is greater than 0.1, which is L of 2 given 1. Here 2 refers to parameter value 2, and 1 still refers to the observation s equals 1. Okay, if we had instead observed s equals 2, let's say if you randomly draw a chip and what you get is a Pringle, then by looking at this table, you see, oh, it seems like F2 supports the observation more. So you would say, okay, theta hat 2 is 2. And if we had observed s equals 3, then theta hat 3 is 1. Right? So that will be the full function, actually. Let me write this down. So theta hat in this example is a function from s to theta, s to omega, and it's given this way. So here this is s, and this is theta hat of s. When the value of s is 1, theta hat returns 1. I just pick the max, right? Pick the max MLE, okay? And in the table format, it would be like this. Let's put that down in our note. Without the commentary, that's our answer. That's the MLE. Okay, so let me just put it in our note. This is example 2.6.2.1. So this is our model. This is our model. S is 1, 2, 3. Big omega parameter space is 1, 2. The model is described by this little matrix F1 of S, F2 of S. S is 1, 2, and 3. The first row is a distribution. In fact, each row is a distribution. The first row goes like 0.3, 0.4, 0.3. Second row goes like 0.1, 0.7, 0.2. So from this model, you can derive the MLE, which is theta hat from S to omega, and it's this little table here. Okay, based on these values. Okay, so theta hat is S theta hat of S okay, when S equals 1 is observed, theta hat 1 picks 1, returns 1. When S equals 2 is observed, theta hat returns 2, and when S equals 3 is observed, it returns 1 again. MLE. Right? This completes the definition of a function, and that's an estimator. This is an estimator. It's a function. All right, let's continue. So note that MLE need not be unique. Yeah, that's certainly true. Let's look at an example. For example, in example 6.2.1, if F2 was denoted as such, so let's say if you change the numbers in the second row so that F2 of 1 is 0, F2 of 2 is still 0.3, and you change F2 of 3 to be 0.3, then suddenly you have a tie in the last column. Right. Then MLE is as given above, right? Theta hat 3 equals 1 is still a valid MLE, but theta hat of 3 equals 2 is also a valid MLE. So MLE is not necessarily unique. Okay, so that's just say, let me put it underneath the definition, right? No a priori guarantee that MLE exists or unique. Okay, remark. In general, no guarantee. Whether MLE exists or is unique. Okay, just bear that in mind. Okay, let's continue. The MLE has a very important invariance property. This is important. We'll see what this means. What do we mean by invariance property? Suppose we reparameterize. If we reparameterize the model via a one-to-one function on psi defined on omega. What do we mean by that? Well, for example, here in our parameter space, we have just two values, 1, 2. We can reparameterize this model by, say, instead of using 1, 2 as parameter values, I'm going to use, say, omega prime equals AB. And 1 maps to A, and 2 maps to B. 2 maps to B. So let's say this is our reparameterization. So in the table, instead of having F1 of S and F2 of S, instead you'll have FA of S and FB of S. And everything else is the same. Same numbers, okay? Same numbers. Just the name of the distribution is now changed to FA of B and F2 of B. And of course, this is what we call an injective function. Right. So it's just a different way to label the potential distribution. Okay, just a way of labeling different distributions in the model. Say, if you do that, should you change your answer? Should you change your answer? Actually, let's call this function, say, 1 to A and 2 to B, to be here we use this big psi symbol. Okay, this is a big psi. Big psi that maps omega to omega prime. 1 to A and 2 to B. It's rather silly transformation. If that's done and no change is made about the distributions, okay, just the name of the distribution is changed, how should theta hat, the new estimator, behave? Well, you just change 1 and 2 to their corresponding new value. That's it. So 1 is changed to A, 2 is changed to B. Because after all, it's just the name that got changed. Because earlier I said 1 is guilty, 2 is not guilty. Right. So it's just different ways of encoding or labeling the model candidates. So it sounds very fancy, right? It's called invariance property. It's really just a silly little property. It sounds almost trivial. Right? Just relabeling the distribution in the model in a one-to-one manner. You reparameterize the model via one-to-one function psi defined in omega. By this we mean instead of labeling individual distribution in the model using theta in big omega, you now use psi in, I don't even know how to read this letter. Can you guys help me out here? Chat, what is this letter? My goodness. The fancy letters. I mean, of course you do need these fancy letters to articulate, but you know, the property is really rather straightforward. Greek letters. Let's learn some Greek letters, shall we? Greek letters in math. What are the letters here? I don't even know. It's not here. Oh, actually here. There is this letter called upsilon. It's such a rarely occurred Greek letter. Looks like a Y. Okay, it's called upsilon. Okay, I guess new knowledge unlocked. This weird looking thing is called upsilon. Do you guys know that? Let me know in chat. Have you seen this letter before? Or have you used it in math or stats or whatever? Okay, so that's a new set basically. That's a new set. It's just the image or the range of the reparameterization function psi. Yeah, so this is what I was saying. For example, in the previous example, you could take psi1 equals A and psi2 equals B. So upsilon is the set AB. And now the model is given by G psi. Right? G psi. Remember, G is just the density. G psi is F theta. G psi is F theta for the unique value theta, such that psi theta equals little psi. There's so many symbols, but so little is said. Right? It's just the relabeling of the candidate distribution in a one-to-one manner. Never heard of it, right? I never heard of this thing. It's called upsilon. Yeah, as I said, new knowledge unlocked. So nothing has changed about the probability distribution in a statistical model. Exactly. This no number in the table is changed here. Okay. Then we have the following result. Okay, this is a theorem. It's a theorem. Of course, it's a silly little theorem, but a theorem nonetheless, called the invariance property. If theta hat of S is an MLE of the original parameterization, remember, for the original parameterization, theta hat is a function here. For the original parameterization, theta hat maps from S to the set omega, right? And now you have, actually, you know what? Let's draw some diagram here. So you have the set S. This is the parameter space. This is the sample space. And this is hold on a second, what is that? Yeah, the big omega, the parameter space. And this is a new parameter space, upsilon. Okay, so S to omega is related. A function theta hat, the MLE, maps from the sample space to the parameter space, the old parameter space. Okay, and the reparameterization function big psi maps the old sample space big omega to the new sample space upsilon. Okay, what the theorem says is that so imagine if you want the new MLE that maps from S to upsilon, call it psi hat. Psi hat is just the composition of the two. Psi hat just equals the reparameterization function psi. Okay, it's just the reparameterization function psi and reparameterization function psi acting or composing with the function theta hat. Composing with the function theta, that's it. Okay, the theorem says 6.2.1. If theta hat of S is an MLE for the original parameterization, And if theta and if psi is a one-to-one function defined on omega, now one-to-one function, remember one-to-one is just injective, right? Which means different input must have different output. And if two outputs are the same, or equivalently, if two outputs are the same, then their corresponding inputs are the same. Okay, defined on omega. Then psi hat of S, the new MLE, equals what? It can be is an MLE, right? It does not say the unique, but this certainly works. Psi of theta hat of S. Okay, let's take a look at the proof. This is a new MLE for the new parameterization. Let's look at the proof. So if we select the likelihood function for the new parameterization to be L star, so L star as a function of psi given S is G subscript psi of S. This looks scary, right? This looks scary, but let's think about what this means. G psi of S is what? G psi is equals F theta for the unique value theta such that psi of theta equals psi. Think about it. Is this well defined? Is the notion of G psi well defined? Well, because big psi is one-to-one, that means if you're given an output, its input is determined. So suppose that psi is in the range upsilon. Then for each psi, there must be a corresponding theta such that big psi of theta equals psi. It's just the property of one-to-one function. So theta is now determined. Given psi, theta is determined. So if theta is determined, then f theta is determined. So this is well defined. Okay, and that's the meaning of the new likelihood function. Okay, and the likelihood for the original parameterization to be L theta of S, so no star here. Okay, so then we have what? Then we have L star. Okay, L star of theta hat of S. Remember what we want to do. Okay, we want to show that the new MLE defined this way is actually the new MLE. So this is greater or equal to all possible L star value, right, for all other inputs in the new parameter set, parameter space upsilon. Okay, so there you go. Here, just use this definition. It becomes G with a subscript of what? Remember, what's the definition of psi hat? Here, we use this definition, so you use the G, but now you need to specify what is psi. Psi is psi hat. And what's psi hat? Psi hat is psi of theta hat of S. There's so many goddamn symbols, but this is actually very intuitive. It's actually just a very intuitive property of just relabeling the parameters. Okay. All right. So here, what is this? What is this? What does this mean? Well, it comes from this equation. Remember how f of theta is specified. Given a psi value, you want to find the unique theta value such that phi of theta equals psi. Okay. So here, because the subscript in G is just big psi of theta hat, of course the corresponding theta is just theta hat. But what is theta hat? Well, theta hat is the MLE, the OG MLE, right? The original MLE, which must have the MLE property. So the original MLE has this property, which is big L of theta hat given S greater or equal to big L of theta given S. But that's just the same as the reparameterized version of L. Okay. So that's just L star. That's just L star of psi of theta of S. Psi of theta given S. So looking at the beginning at the end, we notice that, oh, for this function, L star, indeed, psi hat maximizes the likelihood. So we're done. Okay. Theorem 6.2.1 shows no matter how we parameterize the model, MLE behaves in a consistent way under reparameterization. So it's literally said if you have the MLE under the old parameterization, and now you apply a one-to-one function to it, right? The new MLE is just the reparameterization function composed with the old MLE. Okay, and this is an important property, and not all estimation procedures satisfy this. Actually, guys, this is all well and good. Okay, I have no problem with this whatsoever, but I do quite clearly remember from my own study, earlier study, that the invariance property of MLE does not even require one-to-oneness. Of course, this is still true for one-to-one function, right? We have this proof, but I don't believe the invariance property actually relies on one-to-oneness. Okay, I mean, this is certainly correct, but it feels like we're making a big deal about the one-to-oneness of this function. But I don't think that's actually necessary. Let me just give you an example, okay? So consider the Bernoulli distribution. The Bernoulli distribution of theta, which is the parameter of x equals 1. So suppose xi id. So you have x1 all the way to xn, I equals 1 to n. Okay. My point of giving this example is to illustrate the idea that the big psi function of theta, does not need to be one-to-one. And here's the example. So you can easily show that, we will do that probably in a second, you can easily show that MLE for theta is theta hat equals x bar. That is to say, the proportion of data points that equals 1. Right? Bernoulli distribution either equals 1 or 0. Xi is in the 0 or 1. Okay. The MLE for that model is simply theta hat equals x bar. Okay, so no problem whatsoever with that. But let's say if you want the MLE for the variance, so what would be the MLE for the variance of xi? Well, from the property of Bernoulli distribution, it would be theta times 1 minus theta. I clearly remember from my own education that let's just call this function psi of theta. Okay, let's just call this function psi of theta. The MLE for that is just psi of theta hat, which is x bar times 1 minus x bar. But clearly, this function is not one-to-one. Look at the diagram. This is a quadratic function. And the justification for that, according to my own education, is that we're using the invariance property. So clearly, the one-to-oneness does not play a role here. So if you want to find the MLE even for a non-one-to-one function of the parameter, you would still just substitute the MLE into the new function. This is the example. So my point of this example, once again, I want to emphasize that it should, I mean, of course, this is true for one-to-one function, but my point is invariance property of the MLE should not depend, should not even make that assumption. This is work for general function. Okay, so for that reason, I'm going to take a look at another book by Cassell and Berger. Okay, just give me 1 minute, and I'll find that book and see if I can find what I mean. But because right now I cannot recite the original formulation of the MLE, but I'm pretty sure this is a standard problem in mathematical statistics. Yeah, if you find the MLE for the parameter and for any function, literally any function of that parameter, the MLE for the function value is just the function evaluated at the MLE for the original parameter. Okay, does not matter if psi is one-to-one or not. Let me find the book for. Hopefully we'll find it. Okay, hopefully we'll find Cassell and Berger, because right now my desk is a mess, and I need to see whether it is in Cassell and Berger. I think it should be there. And if not, we will talk to AI about this. Okay, I'm lucky that Casella Burger is right next to me. And guys, by the way, you can just, I mean, it's an open secret. You can Google Casella Burger. It will show up in the result. Casella Burger. Casella Burger. There you go. Yeah, go here, the first link. There you go. Yeah, so I'm going to see whether it's, yeah, you do your own research. I do mine, okay? And we'll see if we can find the invariance property of MLE. Going through the content list, hopefully we will find some commentary on that, because this is such an important principle, man. Okay, so, okay, going to chapter 7, section 2, method of finding estimators, and in particular, subsection 7.2.2 in Casella-Burger. Max likelihood estimator 315. Yes, found it. Found it. So we have the definition of max likelihood on page 3016. And we will see if there's any commentary on the invariance. Yes, indeed. I was correct. I was correct. There's no need for one-to-oneness. Yes, there is no need for one-to-oneness actually. And Casella-Burger deliberately emphasized that the function does not need to be one-to-one. Okay, I think this is a great opportunity to augment this text, because this is, even though true, unnecessary. Okay, so we will, before we moving on to the computation, we will do exposition based on Casella-Burger. Okay, so I mean, I like this sort of dual text approach. One text paired with another one this way. But of course, I think it's probably not possible for a complete beginner to do this, right? If you're learning the material for the first time, like how can you know another text already? But we're not complete beginner, are we? Right? So this must be addressed, because this is super important. While you're still at it, well, I mean, yeah, hi Steve. Yeah, I remember you. Hi Steve. Well, I started like at 7, right? So let's see. Let's at least we'll finish doing this example, and next time we will do more computation, because the concept, man, is so critical. You can just, let's say, what else we can do. So here you can do a bunch of first derivative tests, set to 0, regular calculus exercise. Of course, those are valid exercises, and they're important, and you should actually remember these exercises, the result of these exercises actually, but it's still important to first settle this once and for all. Okay, it is set as, let me just put it in here, invariance of MLE. No, I'm not still going from this morning, okay? I'm not that crazy. And actually this week is very much the anomaly. This week I've been doing multiple streams a day on average. This is because I'm on vacation right now. And starting next week, things will be a little bit different. I think no more than one stream each day. Well, perhaps with the exception on, I don't know. We'll see, okay? We'll do the best I can. So, yeah. This is not like my channel. I mean, of course, I try to maximize output, and not in the sense of spam. Okay, these are actual math. I mean, I don't. Hopefully, nobody would interpret multiple streams a day as spam, because this is me actually working, like, and some with actual math or in certain stream Russian language, right? So I hope nobody, or the majority of you guys, will not interpret this as me spamming content, because this is literally me doing the work. I hope people can still appreciate that fact. Okay, I'm not mean to spam. If you find my posting or streaming too frequent, just simply turn off the notification. But yeah, what I do wish to keep some sort of record, and if those records can help other people, that will be fantastic, like, in my view. And feel free to ignore them. So here we're doing this invariance property of MLE. It says in the Castellan-Berger, okay, I'm reading words from Castellan-Berger verbatim. It's on page 319. Casella and Berger. Page 3000, Berger. Page 319. Okay, let's continue. A useful property of maximum likelihood estimators is what has come to be known as the invariance property of maximum likelihood estimators. Suppose that a distribution is indexed by a parameter theta, but the interest is in finding an estimator of some function of theta, say tau of theta. Okay, so let's say, I'm just going to paraphrase what we just read. So your model is still f theta, where theta is in some parameter space, say big omega. Okay, and now the interest is not theta per se. It's not necessarily the parameter theta per se, but rather a function. The interest is to estimate tau of theta, or more precisely, finding a point estimator of tau of theta, where tau is a function. This is a given function. Okay, so this is all right. This is our goal, and the example I gave here. Suppose you have the Bernoulli distribution, right? Theta is a parameter, and our main goal is actually to estimate the variance. The tau of theta in Castellan-Berger's notation is theta times 1 minus theta. That's a given function. So we wish to estimate that. All right, let's continue. Informally speaking, once again, I'm reading the Castellan-Berger text verbatim. Okay. Informally speaking, the invariance property of MLEs says that if theta hat is the MLE of theta, then tau of theta hat is the MLE of tau theta. Let's write that down. Okay. Invariance property of MLE informally says the following. So if theta hat is the MLE of theta, then tau, the function tau here, tau of theta hat is the MLE for tau of theta. So that's the statement, informal statement. So for example, let's write an example. For example, if theta is the mean of a normal distribution, then the MLE of theta, then the MLE of sine of theta is sine of x bar. If theta is the mean of normal distribution, okay, then and actually let me just complete the sentence. If theta is the mean of a normal distribution, then x bar equals theta hat is the MLE for theta. Okay, this will be proved later. Actually, it's not that difficult to see because I'm just going to quote one of my previous notes. My last notes on mathematical statistics is on July the 25th. Here. Do we have the, or perhaps even earlier? Yeah, actually earlier. On the 19th. Or actually perhaps even earlier. Yeah. Yeah, this is a location normal model. So suppose theta is the unknown mean and the variance of the normal distribution is known. So the likelihood function after some simplification is as follows. Actually, this is perhaps not the useful form, but earlier. Oh, actually, perhaps it's the fourth. Yeah, it's the fourth. Almost a month ago. Yeah. So here, this is perhaps the most instructive version of the likelihood function for the normal distribution, because sigma naught is a constant. This is a constant. So to maximize L, you just need to maximize this exponential factor. And to do so, you just minimize this sum of square. Okay, and to minimize this sum of square. And this sum of square, through a geometric transformation, can be written in a Pythagorean identity. Okay, so this is a Pythagorean identity. Oh, hi, HYZ. So clearly, the first term is independent of theta, and the second term is a quadratic function in theta whose local minimum, well, actually just global minimum, is just x bar. So this is clear. From this is clear that in a location normal model, x bar, the sample mean, is the MLE for theta. Okay, so right now I'm just using that fact here. If theta is the mean of the normal distribution, then x bar equals theta hat is the MLE of theta. Okay, so see the notes for July the 4th. Okay. Okay, so there's that, and then sine of x bar is the MLE of sine of theta. That's it. So that's an application of the invariance property of MLE. Okay, and now we wish to justify that. Okay, so here, I'm coming back to the text by Casella-Berger, and read the main text verbatim. It says, there are, of course, some technical problems to be overcome before we can formalize this notion of invariance of MLE. And they mostly focus on the function tau. Yeah, this function tau. Focus on the function tau that we're trying to estimate. If the mapping theta to tau, let's say if the mapping tau is 1-to-1, then there is no problem. In this case, it is easy to see that it makes no difference whether we maximize the likelihood as a function of theta or as a function of tau of theta. In each case, we get the same answer. Right. So that's exactly what's been dealt with in the main text. Here, we are treating the function big psi as a reparameterization. That is to say, there is a 1-to-1 correspondence between the value of psi and the original input theta. So in this case, it's just, as I said, relabeling of the table's role. It's silly. I mean, it's not silly, but rather it's trivial that the invariance property holds. What we really wanted to overcome is to get rid of this 1-to-1 assumption. Okay, so that's clear. So and then Casella-Berger went on and said, in many cases, this simple version of the invariance of MLE is not useful. Yeah, so theorem 6.2.1 this simple version of the invariance is not useful because many of the functions we're interested in are not one-to-one. For example, to estimate theta squared, the square of a normal mean, then the mapping theta to theta squared is not one-to-one. Right? We've seen multiple examples here. This quadratic function is not one-to-one. The sine function is not one-to-one. Here, sine is not one-to-one. So the theorem we've seen in the textbook is not useful. Now, in Evans and Rosenthal is not useful. So thus, we need a more general theorem and, in fact, more general definition of the likelihood function of tau of theta. Okay, so let's begin. If tau of theta is not one-to-one, let me just summarize the commentary above. Okay, so the case where tau is one-to-one is covered by theorem 6.2.1 in Evans and Rosenthal. So in this case, tau is a reparameterization. Here, tau is a reparameterization. So this case is rather trivial. However, the more interesting case is where tau is not necessarily one-to-one. Here, because case should be non-overlapping, let's just say case is not one-to-one. Right? So in this situation, we need a more general theorem. You need a more general theorem. In this case, you need a generalization. Need a generalization of theorem 6.2.1 above, and you actually need a more general definition of the MLE. Actually, need a more general definition of the likelihood function of tau of theta. And in fact, need a more general definition of the likelihood function of tau of theta. Oh, hi chat. Thank you very much for joining the stream. So if you're new to the stream, we're dealing with the invariance property of MLE. So yeah, and in particular in the case where the transformation of the parameter is non-one-to-one of tau of theta. Okay, so this is what we wanted. And now we come back to the text by Cassell and Berger. It says, if tau of theta is not one-to-one, then for a given value eta, there may be more than one value of theta that satisfy tau theta equals theta. Tau theta equals eta. Okay, actually let me write it down. Okay, in the second case here, if tau of theta is not one-to-one, okay, then given eta, the equation tau theta equals eta may have multiple solutions, more than one solution. Or theta, right? For example, if tau of theta equals theta times 1 minus theta, then it quote-unquote fails the horizontal line test, right? So that's the model, that's the example we got from the binomial example. So this is theta, this is tau, right? Given eta, there are two possible values of theta that correspond to it, 1, 1, 0, 1. Okay, so this is obvious. Okay, so let's continue. In such cases, the correspondence between the maximization over eta and over theta can break down. Exactly. So, for example, if theta hat is the MLE of theta, there may be another value of theta, say theta naught, such that they have the same tau value. We need to overcome this difficulty. Okay, so now we need to give a new definition called the induced likelihood function. So to avoid this difficulty, let's define for tau of theta the induced likelihood function. Define for the function tau of theta the induced likelihood function. L star. This is the same notation we used in Evans and Rosenthal. L star. And L star is given by the following. Okay, so L star of eta given the sample is denoted as x in Cassel and Berger's text. This is but diagonal and horizontal lattice. Actually, I love cupcakes. I'm not sure about that. I'm sorry, I don't understand the comment. Okay, perhaps it's just my lack of understanding. It's totally possible. But okay, yeah, if you wanted to give me perhaps a link for the definition that of what you just said, diagonal or horizontal lattice, I'll be eager to look at. Okay, so yeah, L star, this is a new function. The new function is a function of the values that are attainable by tau. So here, L star, this is defined as the supremum. Defined as the supremum, or if you're uncomfortable with working with supremum, you can consider this as the maximum. Okay, the supremum, because the supremum always exists in this context. Because, I mean, not necessarily actually. We don't even know whether L is bounded, but okay, supremum generalizes maximum. Let's not get bogged down with real analysis here. So yeah, supremum of the function L, little l, sorry, the original likelihood, L theta given x. Okay, so that's the definition, and it is maximized over theta such that tau of theta equals eta. There you go. Okay. Okay, so that's the induced likelihood function. So let's think about what this means for a second, and in particular, perhaps look at some example. This will be helpful. Okay. All right. So once again, let's take our Bernoulli example and put it in our notes. For example, this is our homemade example. So suppose you have x1 all the way to xn, IID Bernoulli, with the parameter theta. Then the likelihood function L of theta given little x would be as follows. This would be the product I from 1 to n and the f of theta given xi, okay, and which will be big pi product I from 1 to n, theta to the power of xi times 1 minus theta to the power of 1 minus xi. And the multiplication gives us, use the law of exponent, just theta to the sum of xi times 1 minus theta to the power of m minus the sum of xi. Or you can write this equivalently as theta to the x bar, theta to the power of x times x, n times x bar, times 1 minus theta n minus nx bar. Right? So that's the likelihood function. So, but anyway, the exponent for both theta and 1 minus theta is just some integer. The sum of xi is the number of ones in these Bernoulli trials, and n minus sum of x1 is, of course, the number of 0. So let's write it this way. Okay. So yeah, here you can say theta to the number of ones equals theta to the number of ones times 1 minus theta to the power of number of zeros. Okay, let's plot the likelihood function. The likelihood function would look like this. 0 and 1. Theta, this is L, theta given x. And now let's consider the transformation. So here, let me just reorganize my notes so it looks tidier. So this is the likelihood. I want to plot the induced likelihood. This is what I want to do. What's the induced likelihood? So now let's consider the transformation, tau, now define for tau of theta equals theta times 1 minus theta. What would be the induced likelihood? Well, let's think about that. So suppose tau equals eta, like this. Suppose tau equals eta, then first of all, what would be the range for eta? Right, so yeah, we first have the range. So tau of theta such that theta, say, is between 0 to 1. I'm going to use closed interval. This is 0 to 1/4. Because when theta equals 1/2, theta, tau of theta is maximized. Draw the picture. We've done that a few times already. Yeah, so this is tau of theta, 0 to 1. So that's the maximum value of tau, which is 1/4. So now let's consider L star as a function from, well, yeah, this is a function of eta where eta belongs to, is in the set 0 to 1/4. Okay. So suppose you have a given eta between 0 to 1/4. Then there should be two theta correspond to it. And what we do on the right-hand side is for these thetas, actually just for these two values, we're going to pick the maximum L. So that's the definition of L star. Sup or max. For this definition, you can ignore their subtle differences. Okay, so this is the definition. This is the definition, and here, yeah. So for, let's say, if you pick eta, so there will be two values. There will be two values of theta that correspond to the same eta. And you're going to plug in those two values into the likelihood function. And you pick the one that is maximized. Okay? There is no a priori reason that those two theta values, say theta 1 and theta 2, will produce the same L value. Okay? Here for this example, tau is symmetric about theta equals 1/2. where big L has no such obligation. Okay, unless the number of ones and the number of zero are exactly the same. In that case, big L would be symmetric about theta equals 1/2 as well. And in that case, L of theta 1 and L of theta 2 would be the same. But in general, they need not be the same, because L of theta do not enjoy, in general, this symmetry. So what the induced likelihood function says, okay, is that for a given theta, for a given eta, you first solve the equation tau theta equals eta, and for these roots, you are going to evaluate the big L at those roots and pick the largest L value. That's the L star value. Okay, so here, I mean, in this construction, okay, in this visualization, the left endpoint, the smaller value of theta, namely theta 1, has the bigger L value on the picture. Let's suppose, okay, suppose L of theta 1 given x is greater than L of theta 2 x. Then in this case, the bigger value L of theta 1 of x, that's defined as L star of eta given x. Okay? Yeah, so let me write down the verbal description of this procedure down here. So the definition of L star of eta given x says, okay, for a given eta in the set 0 to 1/4, you solve for theta from the equation tau of theta equals eta, or equivalently, theta times 1 minus theta equals eta. Of course, it has two roots. In general, right? In general, so if eta equals 1/4, you get repeated roots. Okay, there's in which case you still count as two roots. Okay, but with multiplicity 2. Solve for theta from the equations to obtain, in this case, theta 1 and theta 2. Theta 2. Then evaluate and compare L of theta 1 given x and L of theta 2 given x. Right? And you pick the larger one to be the value of the induced likelihood. To be L star of eta given x. That's the value of the induced likelihood. So it's defined this way. All right. So let me highlight that. This is the definition of the induced likelihood. The induced likelihood is defined verbally as such. So you have the original likelihood L of theta and a function of the parameter tau of theta. Then the induced likelihood induced by the transformation tau of theta, not necessarily 1-to-1, right, is defined as the highest possible value of the original likelihood over theta such that tau theta equals eta. Okay, suppose you're for a given transformed value, the value for the induced likelihood function equals the maximum of the original likelihood function over the value of theta such that tau theta equals the given eta. Okay, it's a little bit convoluted, but I think this example helps illustrate the idea. Okay, so once we have the definition, we can proceed to prove a theorem. So after this definition, Casella and Berger says, the value eta hat that maximizes L star, okay, the value eta hat that maximizes L star will be called the MLE of eta equals tau of theta. Okay, here, definition continues is given by this, and here, definition continues. So what do we mean by the MLE of tau of theta, right? So that's what we're trying to define. The value eta hat that maximizes L star of eta given x, L star of given x will be called the MLE for the MLE of tau of theta equals eta. So that's the MLE of tau. The definition for the MLE of a transformation of the parameter, not just the parameter itself. Okay, so that's the definition. And now let's proceed to prove a new theorem. This is the generalized version of the invariance property given in Evans and Rosenthal, aka theorem 6.2.1 in Evans and Rosenthal. So yeah, that's the theorem. So let me state that. This is theorem 7.2.10 in CNB. Okay, and that's the invariance property of MLE. The general version. Okay, so the theorem says if theta hat is the MLE of theta, then for any function tau theta, the MLE of tau theta is tau of theta hat. For any function, it doesn't have to be one-to-one. For any function tau of theta, the MLE of tau of theta is just tau of theta hat. So this is a very convenient property of MLE. So let's say your original electrical function is maximized, right? And you, for whichever function of theta, its MLE is just a direct substitution of the MLE for theta into the transformation function tau. You don't need to redo maximization again. Okay, so that's the invariance property of MLE. So that's very convenient. Okay, so now let's go about proving the theorem using the new definition, the induced likelihood. Induced likelihood induced by the transformation. Okay, so let's go. Proof. So, I mean, can we set up the structure of the proof, right? We've been doing fundamentals of proof writing. I mean, we did one episode for that. But let's try to apply what we learned over there. The crucial message, perhaps the overarching message of our introduction to proof, which happened, I think, on Wednesday, is that the structure of the proof should be dictated by the structure of the statement, by the logical structure of the statement. Okay, so typically we do so by assuming the if part of the theorem. Right. So does that help us disentangle the statement? Because typically a theorem is a complete sentence. If blah blah blah, then blah blah blah. So simply by writing down the if part, starting with assuming the if part, help us disentangle all of this. Okay, so here, let's just start by assuming assume theta hat maximum is MLE. Well, assuming the if part, right, is the MLE for theta of, assuming theta hat is the MLE of theta, okay, and what do we need to show? What do we need to show? And now, okay, so then, well, this is the then part. So we need to show for any function tau of theta, the MLE of tau of theta is tau hat of theta, tau of theta hat. So because this is a universally quantified statement for any function, right? So let's write let tau of theta be a function. Let tau of theta be a function. Be a function. So this means an arbitrary but now fixed function of theta. Okay, so let tau of theta be a function of theta. So that's the second thing we should write. Now, simply based on the logical structure of the statement. Universal quantifier, let's start with let tau of theta be a function of theta. Right, we need to show that MLE for tau theta is tau of theta hat. Tau of theta hat. So basically, we want to show that tau of theta hat satisfy the property of the MLE. Okay. So need to show. So it feels like nothing is done, all right? It feels like nothing is done, but don't worry, we'll unpack the meaning. Right now, it's just disentangle this sentence. This is what we do. Need to show tau of theta hat is n Actually, you know what? We should use indeterminate article. Okay. Is NMLE. NMLE, because we said nothing about uniqueness, right? If you say nothing about uniqueness, then using the can be misleading. Okay, assuming theta hat is NMLE, is NMLE of theta, and need to show that tau of theta hat is NMLE of tau of theta. Okay, so we're making baby steps towards the final proof. Cool. Okay, so what do we need to do? How do we show tau of theta hat is the MLE for tau of theta? So we can formulate or unpack this sentence as follows. To this end, let say eta star. Let eta star be a value that maximizes the induced likelihood. That maximizes the induced likelihood, big L star of eta given x. And we need to show that the value of L star at eta star equals this thing, equals L star evaluate this thing, tau of theta hat. And we will show, and we shall show L star, the induced likelihood, evaluated at, actually, you know what, let's not call it eta star, let's eta hat. That's the more, perhaps the natural notation. Eta hat given x equals L star of tau of theta hat given x. Right? So you see, I'm not claiming uniqueness here. Okay, just say if eta hat is a value that maximizes L star. Right. Then if you plug in tau of theta hat, you should get the same value. Now, if you can do so, then this end is achieved. Our goal is achieved. Okay, so let's work on this goal. Okay, so let's notice in the definition of the induced likelihood, it is a fact that the maximum, the maxima, actually the maxima, okay, plural, the maxima of the L star and L coincide. The maxima of L and L star coincide. Because this is what we mean. Let's write that down. So L star of eta hat, that is supposed to represent the maximum of the induced likelihood. L star of eta hat given x. This is what? This is by definition. By our definition, the sup over all values of eta, right, of L star of eta given x. This is just the definition of eta hat. And what's that? Well, let's write the definition for L star, okay? So the sup over eta remains, and then this is another sup. So this is a sup over theta such that tau theta equals eta. Tau of theta equals eta, all right? This is just nothing but the definition of induced likelihood right here. And then L of theta given x. Okay. Right. And my remark earlier is that L star and L, because you're maximizing the same function, this should equal the maximum value of L. So think about it. Okay, let me finish first writing this. So this should be the max of L of theta hat given x. This should be the same. Actually, let me add an extra step. Okay. And let me add an extra step to be extra clear. This is just the sup over all theta of L theta given x, which equals L of theta hat of x. Right, think about this. Right, these two should be the same. The two maximum values should coincide. Or the maxima, right? We don't know a priori the maximum is unique, right? The maxima of L star and L should coincide. Here, this is what we're doing in the very first line. So suppose you have a fixed eta, right? And you set tau theta equals eta, solve this equation, and you get a few roots for theta. Compare which one is the biggest, and pick the biggest. That's this part. And then you're doing this over all possible values of theta, all possible values of eta. Because eta is just a point in the range of tau. This is the same as maximizing the function L of theta given x directly over the set of the original parameters. So these are the same. Okay, yeah. Here, of course, we're using in the last step we're using the definition of theta hat. Okay, so there's that. Let's add a verbal description of this derivation. What we're doing here is that notice that the maxima of L star and L coincide. note that the maxima, this is once again something we wish to come back to in our proofwriting intro. In some derivation, especially long one, it is a good idea to summarize the purpose of the derivation. You have a bunch of equality going on. To summarize the purpose of the definition above the derivation. Okay, note that the maxima of L star and L coincide, meaning coincide, meaning the following. Just some this will help with the readability of the proof. Okay, so this is something that we notice. Remember what we want to do, right? So we want to show this is our new goal. This is our new goal. We wish to see, okay, this is the same as L star of tau of theta hat. So we start from the left hand side and we wish to get to the right hand side. Okay, so this is the meaning. And now let's continue. So yeah, here perhaps I should explain this step. I just explained this step, the star step, verbally, but let's put it in the proof as well. So star follows because the iterated maximization equals the unconditional maximization over theta. Follows because first you have iterated maximization. Because this is the most notationally heavy step, I wish to make sure this is absolutely understood. Let's give another concrete example so that there is no misunderstanding over the step star. Let's think about the real life scenario. So let's say if you want to find the country, actually, so let's suppose you want to find the biggest area of a country. Among all the countries in the world, okay, you want to find the highest value, the maximum of a country's area, territorial area, right? So if you want to do that, of course we know in our universe it's Russia. Russia has the biggest land territory. So I mean, suppose our goal is to find not the country that has the biggest land area, but just the largest and land area itself. We want to find the maximum value of the land area. It's a number, okay, not a country name. Think about how would we do that? Think about how we do that. So we can do this in this manner. Okay, let's define a function. Let's define a function called tau. Tau takes a country. So theta is a country. So tau takes a country and returns the continent where the country is located. Okay, so tau of theta is the continent of the country. Okay, and I suppose this is well defined. Okay, I know Russia is both in Europe and in Asia, like all of those others. Let's suppose in our reality that each country uniquely belongs to one continent. Right, and tau is the function that returns the continent. So you can do this for each continent. So suppose that now, because eta is the value of the continent, so you have how many values? Well, you have starting from Asia, Europe, Africa, Oceania, North America, South America. Well, maybe Antarctica, but there's no country, so we ignore that. Okay, so these are the possible values of eta, or the continent. You can maximize area in each continent. So say, let's just assume Russia belongs to Europe. Okay, in Europe, the biggest country is Russia, and you take its land area. Okay, and in Asia, the biggest country is China. In terms of land area, okay, you take the area for you take that maximum to be the area of China, and then you go to Oceania. Oceania, that will be the largest country will be Australia, right? So you take the area of, you record the size of Australia, and you do this over each continent. But North America, that will be Canada. You get the idea. South America, Brazil, and Africa. Actually, I don't know, so it doesn't matter. Okay, so now you have the collection of the largest land area of a country in each continent, and then you just soup over them. So now you're comparing the maximum of the largest area in each continent among all continents. And guess what? That maximum value is the same as the maximum value if you just disregard the continent information and you just soup over the whole world. It should be the same value. Right? So there's really no mystery going on here. So this star might look a bit notation heavy, but really there's no mystery here. The maximum should coincide, or the star step follows from the real world, not analogy, but an application, literal application of this principle. It follows from this principle. The iterated maximization equals the unconditional maximization. Hopefully this is clear. Okay, just want to make sure there's no mystery going on here. Okay, so what else do we have? So we want to get to the right-hand side. Can we say this is the right-hand side? Let's think about it. Let's think about that. So what is L of theta hat? We have this. On the other hand, furthermore, L of theta hat given x is what? L of theta hat, by definition, is, because I want to show these two are the same, right? So first of all, what is L star? I want to, let's say, go back to this goal here. So let's perhaps start from here. Let's say, what is L star of tau evaluated theta hat? L of tau evaluated theta hat given x. That's induced likelihood. Induced likelihood, use the definition. Use the definition of induced likelihood right here. Compare that. Let's not forget the definition of L star. Okay, so yeah, this would be, just substitute theta in there. So this would be the soup over the set theta equals tau of theta equals tau of theta hat of L theta given x. This follows from the definition, or definition of L star. Okay, so now I'm starting from the right hand side now, and let's think about what this is. Think about what this is. So I'm considering the supremum of L of theta given x, where theta satisfies this condition. Where theta satisfies this condition. So hang on. What do we want? What we want this to be this one. To be this one. So here you're not theta hat. What does theta hat satisfy? Well, theta hat satisfies this property, right? Theta hat satisfies this property. That is, L of theta hat given x equals the sup of L given x. Because theta hat is the MLE, theta hat is the MLE, so it maximizes L. Theta hat is MLE, so it maximizes L. And so now you want to maximize L. Now you're maximizing L, and the theta you're considering are the theta that satisfies tau of theta equals tau of theta hat. But you already know theta hat maximizes L. So among these theta, among this little subset of theta, because it contains, obviously theta hat is in this set. So looking at this set, it is trivial that theta hat belongs to this set. So you're maximizing the L function over a subset of theta, which includes the unconditional maximizer. Remember, theta hat is the unconditional maximizer. Although all possible values of theta hat gives the largest value of theta hat. And now you're maximizing little l, maximizing big L over a subset of the parameter space, which contains the unconditional maximizer. So this is just big L of theta hat. Okay, so hopefully I'll explain it again, okay, in a shorter way. At this step, we are considering the maximum value of L of theta given x. What do we know about the maximizer of this function? Well, by definition, that's just theta hat. That is to say, over all possible values, over the set of all possible value of theta, L of theta hat gives the maximum value. And what is the set over which we're maximizing here? Well, obviously it is a subset of the parameter space. And this subset contains theta hat, the unconditional maximizer. Theta hat trivially belongs to this set. So you're maximizing over a subset of the parameter space that contains the unconditional maximizer, and therefore the maximum value for this, the maximum value over this subset is just the unconditional max. So now we have our goal, and we're done. Okay, so I know this is a bit of a mental gymnastic and convoluted, but this is a fundamental property of MLE, which warrants a rigorous proof. So by comparing 1 and 2, we have what we need. And that's QED. And we're done here. So we have what we need, and let's conclude. Hence tau of theta hat is an MLE of tau of theta. And that finishes the proof. So the original assumption in the theorem 6.2.1 by Evans and Rosenthal, the one-to-one requirement is now removed. You do not need that. And indeed, for most application, this assumption is not true. So removing this assumption does not hurt us. Okay, so there's that. Okay, and this concludes the statistics part of this live stream. Okay. So we did this part of the main text and quite substantially extended theorem 6.2.1. So I'm quite happy about that. And now let's move on to the next part of the stream, in which we will discuss the fundamentals of exterior ballistics, and in particular the foundations of 6 degrees of freedom models. Okay, 6 degrees of freedom for modeling the projectiles dynamics. Okay, which will be an entirely different topic. So just to keep us on the same page, what we're trying to do here. Actually, you know what, guys? I think I find a good illustration, a good visualization, a much better picture than I can possibly draw. It's a description of the 6DOF model published by Finnish ammunition manufacturer called Lapua. 6DOF model Lapua. So it is advertised that Lapua nowadays use 6DOF for their table calculation, the range table calculation. Okay, so let's see what commercial providers have to say about this model. Chat says, are you familiar with the concept of a profile likelihood? I'm not quite sure. Actually, you know what? Why don't we check that out? Profile likelihood, I don't know. Okay, there's so many variations and extension of max likelihood estimation. So profile likelihood. Profile likelihood is a method used to estimate a nuance parameter and evaluate a specific parameter of interest. It works by fixing the target parameter at different values, maximizing the likelihood function over the remaining parameters for each fixed step, and plotting the max value max value to perform inference. Okay, you know what, guys? HYZ, let's try to write some notes over this, because this is new to me, and let's figure it out. So profile likelihood, is there a good note? Definition of profile likelihood. Okay, this is always a good idea to look at the stats community. So this is what it says. Okay, so this is in literature, but here let's just write. Let's see what the community has to say. This is a good number of upvotes, so chances are this is useful. Let theta be a vector parameter that can be decomposed as theta equals delta zeta, where delta is a vector parameter of interest and zeta is a nuisance of vector parameter. So the thing is, often in estimation problems, you have a main parameter of interest, so to say. Like the simplest example would be, you know, guys, in what we call the T statistics, right? T statistics or T statistics based inference. What you really care about, like in the T test, is to study the mean, right? Yeah, the induced likelihood is basically the special case of. We'll see about that. Okay, we'll see about whether the definition of induced likelihood in Cassell and Berger agrees with what we have here. Okay, so the setup, the basic setup here in the in the profile likelihood is as follows. You have a full parameter theta, which can be decomposed into a nuisance parameter and the main parameter of interest. Right? For example, you can think of in a normal model, you only care about the mean, but you still don't know the standard deviation. So the standard deviation is a nuisance parameter. Right? You don't know it, right? You have to estimate it to fully specify the model, but it's not your main parameter of interest. And for example, in a t-test, the hypothesis is purely about the mean, although you still don't know the standard deviation. So that's the situation. This is, you are interested in only some entries of the parameter theta. Then the likelihood function can be written as such. Okay, L of theta semicolon y equals L of delta zeta semicolon y, okay, which is the density, right? F of y semicolon delta zeta, where f is a sampling model. An example of this is the case where f is a normal density. Yeah, I was saying that f is a normal density, y consists of n independent observation, zeta equals mu sigma, and say you're only interested in sigma. Okay, that's also possible. Let's say you're only interested in the spread. So the mean is the nuisance parameter. Okay, the profile likelihood of the parameter of interest is defined as follows. So LP, P stands for profile, of delta. So let's say delta, yeah, because you want the profile likelihood to be a function of parameter of interest only. So LP of delta. LP of delta is defined as the sup over zeta of L delta zeta y. You see, here we're maximizing the likelihood over, okay, we're treating delta as fixed. We're maximizing the likelihood over the nuisance parameter set. So now there is, on the right hand side, zeta is gone. Okay, so that's the profile likelihood. And how do we work with that? Sometimes you're also interested on the normalized version. Okay, so yeah, it's like you're converting this into a relative likelihood or likelihood ratio, right? So that's what you're doing. Okay, so this is a definition of profile likelihood. So HYZ says this is basically the same as as induced likelihood, or an induced likelihood is a special case for that. Let's see about that claim. Well, I think not quite, but thank you for bring this notion into my. I think I must have used this at some point in my study, but or in actual real world application, but I didn't know the name. So yeah, it's a very natural idea. You sum over, not sum over, but maximize over the quote unquote nuisance parameter. But in the induced likelihood function, there is no nuisance parameter, right? Theta is the full parameter, and you want that, right? And tau actually here, can you think of this way? Can you think of the tau as a projection? Can you think of tau as a projection? So the full parameter is theta, right? HYD. So I'm trying to recast the definition of induced likelihood into this setup. So let's say induced likelihood function uses is essentially induced likelihood function. Can we think of this as some sort of projection, or is it, or actually, guys, is this? I think profile likelihood is a special case of induced likelihood. I think. Because in this setup, okay, you can define your induced the transformation to be tau of theta equals delta. It's just a projection of theta. And now you're souping it. Now you're souping it over zeta. That is to say, the second coordinate don't matter. HYZ says, yeah, we always introduce a new nuisance parameter, lambda of theta, to make it h. H goes from theta to theta, tau of theta, lambda of theta, to be a one-to-one function. In this case, the induced likelihood is just the profile likelihood after maximizing out lambda. I think we're getting there, right? So I was, so HYZ, hear me out. Did you, so was I clear? So I was saying that in the original model, in the original model, yeah, so you have the full parameter theta. And let's write the likelihood function as L of delta zeta, where delta is the tau. Where delta is the tau of theta, and the other parameter zeta, well, you simply don't care. You can let it to be whatever you want, right? The tau is simply the first coordinate, and zeta can be whatever. Can be whatever. So, and now you're just maximizing the irrelevant, maximizing over the irrelevant coordinate, while keeping the first coordinate delta the same. This is exactly keeping tau the same. So perhaps a more accurate statement would be the profile likelihood is a special case of the induced likelihood, where the induced likelihood is induced by the projection map. Tau is just the projection of the coordinates. Right? So if your theta has a bunch of coordinates, you project only the ones that you care about. Yeah, this is an excellent point. But I think it's perhaps more accurately stated as profile likelihood is the special case, is a special case of the induced likelihood, where in the profile likelihood, the transformation is a projection. Yeah, thank you so much for bringing that to my attention, man. Thank you so much. This is an excellent comment. I don't know, like I'll credit you once again in the chat. Like you told me, yeah, this week earlier about the counterexample in the what's that? The measurability of functions that takes values in the extended real. Yeah, thank you once again. Thank you very much. Yeah, this is an extremely valuable comment. I never thought about it, even though I probably used the profile likelihood, what's essentially equivalent of it at some point. But this is an excellent comment. So I'm going to write down the, perhaps I'll put the link here, okay, the link in the, as well as the screenshot in the note. Okay. This is an excellent piece of comment. Thank you so much. This is great. Okay. So remark, the profile likelihood is a special case of the induced likelihood, where theta equals, here using notation delta and xi, and tau of theta is just a projection delta. Oh, no worries, no worries, my pleasure. Well, thank you, my friend, for connecting this important notion. Okay. Well, thank you for, yeah, certainly. I mean, I'm glad that I have this excellent community to help me improve. You know, this is amazing. Okay, so hopefully there's now we hopefully the bottom line is hopefully we now have removed the doubt over the invariance property. The transformation tau of theta need not be one-to-one, provided we define the MLE for tau of theta in the induced likelihood sense. Okay, and this is a concrete example of how induced likelihood works, and this is the new proof. Okay, so thank you guys. Thank you in particular HYZ. I'll add you in the, hold on, let me delete this. This is unneeded. So we will continue with the rest part of the stream. So we're drastically switching topic. Okay, so we're now going to do some classical mechanics. So this is a non-technical description of the 6DOF method by Lapua. So here, this is another, oh, actually it's not found anyway, it doesn't matter. So here, this is the diagram. We're considering the projectile as a rigid body. Okay, considering the projectile as a rigid body, and this is the so-called angle of attack. And what happens is that the trajectory of the center of mass often make an angle with the axis of symmetry of the projectile. And this affects the gyroscopic stability of the projectile. Okay, so the rotation about the axis of symmetry of the projectile is called rho. And we can create an orthogonal coordinate system that is fixed to the projectile and call them the pitch and yaw axes. Okay, so here this is up. The yaw axis points up. So imagine you're treating the projectile as fixed, okay, as fixed. So as stationary. So this is the lab, not the lab frame, but the moving frame. This is a moving frame. So up points up, well, yaw points up, and pitch points left. And the origin is at the center of gravity. So this is a motion that we track. We track the yaw, pitch, rho, as well as the 3D coordinates, or the trajectory of the center of mass in 3D space. So that's why it's called the 6DOF model. Okay, so this 6DOF model has certain advantage. Let's read it from the industry. So 6DOF, as most LaPoule ballistics users already know, LaPoule ballistics applies the 6DOF calculation to model flight paths for LaPoule trajectories. 6DOF is also the calculation model used by LaPoule product development. So what are the advantages of 6DOF, and what does it mean for shooters requiring accuracy? First, let's take a look at some other means of modeling flight paths. The 3DOF. The 3DOF is perhaps the most common, perhaps the most widely adopted method during and before World War II. The 3DOF model, and it's still widely used nowadays for less accurate application, like for example a handgun. Right? It typically does not require long-range accuracy, so 3DOF is completely accurate there. So 3DOF point mass solution. The 3DOF calculation model considers only the drag coefficient, the CD factor. So yeah, just as a brief recap, the CD drag coefficient for projectiles. It is a empirically determined function. So it is a function. It is a dimensionless number. Okay, it is a dimensional number that is a function of the Mach number. Okay, there you go. This is the graph. The horizontal axis, the independent variable, is the Mach number, namely the projectile's speed relative to the speed of sound. Okay, because the speed of sound can be a variable. The speed of sound in general depends on the temperature. So depend on the temperature, and I believe as well as density of air, speed of sound. Okay, so anyway, the Mach number is a dimensionless number. The drag coefficient curve depends on the shape of the projectile. So these are standard projectiles. They do not correspond to any particular real-world projectile. Say they're mass-produced projectiles, but these are more like benchmarks. Okay, I don't know any particular, say, a real-world projectile that corresponds to any of them precisely. Say G1, G2, and whatnot. G1 is the oldest version, and nowadays G7 is the industry standard for example, intermediate cartridges such as the 5.56 NATO rounds and the Russian 5.45. Yeah, just intermediate cartridges used in, for example, M16 and AK-74. And these are their drag curves. And so as you can see, G7 curve has this characteristic that in the subsonic region, the drag coefficient is extremely stable. So over there, you pretty much have Newton's quadratic drag law there. So the drag force is proportional to the speed of the projectile. And of course, you have this spike near Mach 1. So that's the transonic region. So transonic region is typically avoided for small arms design because this causes tumbling. this spike in the drag coefficient causes a lot of instability. So that's why we tend to avoid this. Okay, so basically, when it comes to designing effective range of small arm projectile, rifle calibers tends to stay in the supersonic region, whereas the like for pistols and submachine guns, traditionally stick to the subsonic region. Okay, such as the 45 caliber 45 ACP and the German 9mm parabellum round. So we tend to avoid this region. So now this is a simplification of reality, of course. So the aerodynamic information is summarized in this function called CD of Mach number. So here what it says, okay, I'll catch up to chat in a second, and we'll actually just finish reading this passage. Just the advantage of 6DOF. The 3DOF point mass solution. 3DOF calculation model consider only the drag coefficient. That was the CD we talked about. Using 3DOF does not require a large computing facility. Exactly. You don't need a lot of data. You just need the CD curve to do the numerical integration, the standard Runge-Kutta. Okay. As the name implies, there are 3 degrees of freedom, translational components tracked in the equation. So we're treating the projectile as a point mass. So there's no roll, yaw, and pitch. Okay, just the point mass position, just the point, the center of gravity position. And now we have so back, forward, backward, left, right, down, up, right. 3DOF calculation does not take any stance on the attitude, the orientation of the projectile relative to the directional motion. So this orientation, so this is the axis of symmetry of the projectile relative to the direction it is moving. It is called attitude, and attitude is ignored in the 3DOF model, understandably so. Or the stability of the bullet, right? So because if it's just a point mass, and the stability has to do with the orientation of the projectile very much. You cannot discuss stability in the 3DOF model. And it has a very straightforward and simple approach to crosswind. So imagine if you have a wind blowing in the orthogonal direction of the trajectory, then you would need to apply a differential correction to the trajectory, right? Understandably so, because the drag force is always calculated relative to the surrounding fluid. Right? So if there is a wind, then it would affect the relative velocity of the velocity of the projectile relative to the fluid. Right? So the crosswind, right, of course, we know that from common sense, the wind would blow the bullet away. Right? Give a the wind will a crosswind will give an extra deviation of the bullet's path. So it has a simple approach to crosswind. This means that the 3DOF model calculates the position of the bullet as a function of time reasonably correctly as long as the flight is stable, and that's the main field of application. In windy or changing conditions, however, this model is not the most reliable. And this is why, by the way, I'm introducing an interjection for artillery rounds. Because the travel time of an artillery round is so high, 6DOF model is nowadays absolutely necessary. So because an artillery round typically travels over the course of over a minute, right? And in those procedure, in those process, like the spin, the effects of spin will accumulate. There will be a drift caused by this yawning, this rolling motion here. Okay, so and for those projectiles, due to the range of engagement, you must take into account of the extra drift caused by rolling. Actually, nowadays, modern ammunition, I believe it's called Excalibur. This is a relatively new round, Excalibur shell. Excalibur shell has this unique property that it deploys fins mid-air, so it cancels out the spin. So when it was launched from the projectile, because the barrel is rifled, so it spins when it leaves the projectile, but in the mid-air it will deploy spin to cancel out the spin. Okay, it deploys fins to cancel out the spin. So in the mid-air, at some point, perhaps at an optimal moment at which the projectile is most susceptible to instability, the fin is deployed and it cancels out the spin to increase accuracy. And also, these spins are controlled by GPS. So even though the projectile itself is not powered, it's not a missile, it still has this guidance capability. So you can, the spin is automatically adjusted according to the GPS data. So it is GPS guided, and it is currently now used in Ukraine. Now it is currently now used in Ukraine, but because it is GPS guided, it is primarily GPS guided. The Russians have been using GPS jammers against the Ukrainians, and it is reported that the accuracy of Excalibur rounds suffered because of it. So there is this, and so in that event, it will be supplemented by the inertial guided system. So I don't know whether GPS or inertial guided ammunition are used in parallel, or it uses GPS as a primary guiding mechanism, and then inertial guided technology as a backup, because this is often the case in modern transportation. Say let's say like nowadays in your phone app, like your Google Map primarily uses GPS. However, let's say if you're in a tunnel, then GPS would not receive good satellite data. In that case, then it would be supplemented by inertial guided system. I don't know if this is a case for Excalibur, but it is reported from the battlefield in Ukraine that Excalibur suffers from poor accuracy due to Russian GPS jams. Okay, and as far as I know, the Russians don't have an equivalent system. Okay, they have their own precision-guided artillery rounds, but it requires a human spotter. I mean, whereas Excalibur is fire and forget. So, I mean, the main point is that Excalibur has this property that it can deploy the spin in the mid-air, fins in mid-air, to cancel out the spin drift. Okay, it is much more expensive than traditional artillery round, of course, but it is still much cheaper compared to a guided missile. So this is somewhere in between. The cost is somewhere in between. It's more expensive than a dumb artillery shell, but it is less expensive than missiles. So there's So you see the average cost of this little round is over $250,000 per unit. Okay, actually it was reduced here. I don't know how much. I think it was like about $10,000 to produce one 152 millimeter ordinary round. So this is like 7 times more expensive, but it's still much cheaper than, say, a Javelin or a HIMARS rocket. So so before, of course, you don't have this spin canceling technology. But this is some interesting new development or actually already not development, but already applied technology in the exterior ballistics. Okay, so saying that this means the 3DOF model calculates the position of the bullet as a function of time reasonably correctly as long as the flight is stable. In windy or changing conditions, however, this model is not the most reliable. The modified point mass solution, that's an improvement, Modified point mass calculation, sometimes referred to as the 4DOF, is more advanced than the 3D model. And the calculation includes 3 translational degrees of freedom and 1 rotational degrees of freedom. That's spinning. The aerodynamic model also includes the contribution of the lift force. So this will be covered in future. That's the complete description of aerodynamic force and torques acting on the projectile. So it's actually a lot more complicated than just the drag function CD. Okay, a lot more complicated than this, and you need multiple drag curves. So not just CD, but other kinds of C to describe other kinds of drags. All right. So here we were here. Yeah. Also include lift force. So later, not today, but later we will discuss the exact kind of aerodynamic forces and torques acting on a projectile. There are some of the same forces. There are some of the same forces that the 6DOF model calculates. However, the point mass model applies a simplified calculation which does not take into account the actual attitude of the bullet. Okay, but merely includes an algebraic approximation, pitch yaw angles of the projectile. Due to some simplification involved, the model is not able to give information concerning flight stability. Okay, so that's an improvement. So you have the 3DOF, the most basic version, and the 4DOF, aka modified point mass, and also 6DOF. Why 6DOF? The above-mentioned calculation solution obviously usable for trajectory calculation. So the question is, what does LaPoule Ballistics 6DOF solution offer? The easy answer is the most accurate results. As with the modified point mass model, the 6DOF calculation includes 3 translational degrees of freedom and 3 rotational degrees of freedom, which gives the position and attitude as a function of time. So it tracks all 6 degrees of freedom. Simplified, 6DOF tracks both the pitch, yaw, and roll, as well as up, down, left, right, and forward, backward movement of the bullet. All right. The big difference to the other calculation model is that the 6DOF model of the actual trajectory path of the projectile at all times during the flight. Okay, instead of just calculating the points on the trajectory curve, the stability property of the bullet are obtained during the trajectory integration, since all the rotational degrees of freedom are present in the simulation. So the stability analysis of the LaPoule ballistic app is more advanced than other calculation. It considers both the dynamic SD and gyroscopic stability SG factor. Not only the latter as many other ballistic calculators do. The SD here, gyroscopic stability. SD is especially important in long-range shooting for analyzing transonic stability. That's what I was talking about in the drag curve earlier. Yeah, in a transonic region, projectiles are especially susceptible to instability. Okay, so traditional small arm design tends to restrict their range of engagement to be strictly subsonic or strictly supersonic. This way you avoid this problem. But for extreme long-range shooting, this is unavoidable. So basically, if you, let's say, set your the speed, if you set the speed of over the entire course of effective range to be less than Mach 1, if you do that, then the range would be too short. Okay, then the range would be simply be too short because you don't have enough velocity. Okay, simple as that. So if, let's say, if you set your effective range to be entirely supersonic, the problem is the initial drag would be so large that if you still want to achieve a respectable range, the initial velocity would be something like a railgun, which is also impossible. So for long-range shooting, the transonic region is unavoidable. So not only this is challenging mathematically, it's also a challenge physically, because the accurate physical modeling in the transonic region is very complicated. Mathematically speaking, it's because the aerodynamic is described by a mixed type PDE. Okay, this morning we had a PDE stream. We didn't have time to discuss classification of PDE, but basically you can, for linear second order PDE, you can classify them into elliptic PDE, parabolic PDE, and hyperbolic PDE. So hyperbolic PDE are like wave equations, and elliptic PDE are like Laplace equations. So these are the prototypes basically. The thing is, in the subsonic region, the partial differential equation for describing aerodynamics is elliptic. And in the supersonic region, it is described by hyperbolic. So in the subsonic region, you have little to no shock wave, and you have pretty much a full shock wave surrounding the projectile in the supersonic region. But in the transonic region, things are weird. Okay, so in a certain part, so transonic flight, let me just do a picture. Transonic flight, you have this mixed flow. That's the main physical challenge. So transonic flight, and so shock wave and steady flow. How should I put that? So so just say transonic flight wave profile over projectile. Hope that's a good description. Yeah, this is the physics going on here. Oh, but this is purely supersonic. This is supersonic, not transonic. Yeah, so this is in the transonic region. So you have non-shock wave in the wake, but shock wave at the tip. Okay, this is different compared to supersonic. Right? This is supersonic. Actually, it's a good comparison of these two images side by side. The key difference is the wake behavior in the supersonic and the subsonic regime is different. Okay, is different. So this causes instability because you have different types of waves surrounding the projectile, and which causes instability in the transonic region. It was first discovered by a World War II pilot. When they reach the transonic region, they feel their airframe, the airframe of their aircraft, okay, and the wings are vibrating at a much higher degree. So that was the original discovery there. Okay, so that's why this SD stability factor is especially important in long-range shooting for analyzing the transonic stability of the bullet. Right. So yeah, this is true because here it says, how can the Lapua ballistic utilize 6DOF? 6DOF was theoretically developed even before World War II, but back then there was not reliable methods to estimate many of the complicated kinds of drag coefficient, not just CD. Okay, so if there was no data to fit the model, then the model is kind of useless. So it remained useless until I think mid-1960. And nowadays this is the industry standard, at least for artillery rounds. For small rounds, Lapua apparently uses 6DOF, but there's still a lot of application of just 3DOF. Okay, but 6DOF is the standard in artillery rounds. So that's pretty much where this is applied. But theoretically, you can apply this to any kind of cylindrically symmetric projectile. Okay, and that's this sort of non-technical overview of this method. Okay. Anyway, let me come back to chat. advice for first year. Sorry if you guys asked this question like years ago. Advice for first year. Like, you mean first year university? I would say, of course, get good grades. I mean, that's totally a trivial statement. So I was saying that if you want advice for first year, perhaps is getting good grades should be your first priority. Well, at the same time, try to build connections, because at the end of the day, math is rather a social community. It's a social activity. Okay, of course, a lot of the progress is made on your own, but you wanted to stay connected. I guess that's all I can offer, or kind of advice I can offer, because I feel like, from my own perspective, I didn't do that. I didn't do enough of that when I was in a uni. Okay, I pretty much just go to class, do the assignments, and moved on. To be fair, there's a lot of pressure when it comes to grades and whatnot, but I think it's not in conflict with building connection, even from the very first year, because it makes you work more efficiently. It helps you to work more efficiently, and helps you realize what you really want to do at an early stage. So yeah, I guess that's my advice. There's not a whole lot of advice. It sounds simple, but it's not very easy to do, considering competing interest and perhaps time pressure. I guess, yeah. Try not to neglect the social aspect of studying mathematics. HYZ, well, my understanding of stochastic calculus is rather, I would say, perhaps not the most rigorous, but I thank you very much for your appreciation. But I do wish to say, at this point, try to understand the book on stochastic calculus by Schreff. Okay, not the financial math book by Schreff, but actually the stochastic text by Schreff, the full rigorous version of it. So I'm still kind of grinding through it right now. But yeah, thank you very much. Can you tell us how you study math so many hours a day? Because I'm on vacation right now. That's why. Like, studying math is all about consistency. I think, in my opinion, it's all about consistency. Like, this week is pretty much the anomaly, but when I was in regular days, I still try to reserve an hour or two, and pretty much just do the same thing I do on live, but just myself. But it was, it's like later on I decided, okay, I'm doing this by myself. I might as well show it, right? I might as well show it. And it's simple as that. Perhaps other people will find it useful. Yeah, I guess the thing is, I don't want to. Oh, sorry, guys. I don't want to fetishize, fetishize academic obsession. I don't want to fetishize that. Okay, certainly studying math requires a lot of time, and it is totally legit if you decide there's other priorities in your life that is more valuable. It's entirely okay. So, this is just me, and I find this is the most overall long-term cost-effective way to study math. Because if you say don't do math consistently, and then you come back, you have to relearn what you learned earlier, and it's really frustrating. So I figured I just might as well spend some time every day. Okay, I don't expect to make progress every day, because usually progress is nonlinear, right? Usually progress is nonlinear. It's like you struggle, and at a certain point, boom, it's all clear, or at least most of it is all clear in an area, and then you move on, and you struggle, and then boom, jump. So it's like that. But to reach the critical threshold requires a lot of patience and time commitment. It's just the way it is. I'm used to it, so I guess that's the explanation there. But thank you so much, Kraken. Okay, so with the big picture out of the way, what would be our approach to understand this? I mean, of course, the simplest exposition would simply give out, okay, this is the equation of motion, and this is the numerical method to code this up. Right? That'll be one way to do it. For engineering purpose, that's totally accurate, but we wish to understand the fundamentals from the ground up, and we do not assume extensive background in both classical mechanics, aerodynamics, or numerical methods. So we're going to do things slowly, just like what we did in other series, pretty much. So last time we derived the equations of motion and relative dynamical quantities such as kinetic energy, angular momentum, and whatnot for a system of particles. For a system of particles, not just rigid body. Okay, so that was a while ago actually, which was, when is that? 7/25. All right, July the 25th. So we did. This is a brief walkthrough of what we did last time. So this is called classical mechanics towards Euler's equation for rigid body motion. And rigid body is defined as a system of particles whose pairwise relative distance remains constant. Okay, and here we have the Newton's law for the linear momentum. Basically, the time derivative of the total linear momentum equals the sum of external forces acting on the projectile. Okay, no internal forces is needed because of Newton's second law, they cancel. All right, so, and you can also define angular momentum, the total angular momentum of the system of particles relative to a point. Okay, and the law for that is as follows: relationship between angular momentum and torque. Not with torque, but and torque, between angular momentum and torque. All right, so that's the hold on, what's going on? Yeah, it's now lagging. Okay, and torque. So, and the result for that is as follows: the rate of change of the angular momentum is the total external torque. Once again, only external torque is needed because the torque by internal forces also cancel. Okay. So next we discuss two perhaps subtle notions. Okay. One is called the absolute moment of momentum, and by that we mean the following. So imagine you have a fixed coordinate system with a fixed origin, of course, and an arbitrary point Q. The point Q might be moving. The point Q might be moving, okay? And you can define HA of Q, that's the so-called absolute momentum, absolute moment of momentum, as follows. So just like in the angular momentum, which is basically linear momentum cross with the radial vector. Here, the radial vector is taken as the displacement or the position vector relative to Q. This is Rj minus Rq. So that's the radial vector. And cross with the linear momentum, that is absolute. Okay, so this Mj, mass of particle Mj, times r dot I is relative to the fixed coordinate system. So this is the arm relative to Q cross absolute momentum, absolute linear momentum. So that's why it's called the absolute moment of momentum, which we denote as HAQ. And by defining the center of mass and then taking time derivative, we get this expression. So HAQ dot equals what? Equals minus big M, that's the total mass, times RQ dot cross with RC dot. Okay, RQ dot is the speed, or sorry, the velocity of Q. Remember, I said Q can be a moving point. So that's the velocity of Q, cross with RC dot, where RC dot is the velocity of the center of mass relative to the fixed origin. So you have this term. And the last term is what? The last term is the total external torque relative to the point Q, LEQ. Okay, the external forces crossing with the arm. Okay, so that's the total external torque relative to the point Q. And that's the equation here. So if we specialize Q to be any of the three following scenarios, in which I think, hang on, in which the third one is perhaps the most important. In which the third one is perhaps the most, in the third occasion, okay, in the third occasion, it says when you have, so basically you want the cross product in the first term to vanish, okay, and for that you have a bunch of possibilities, either R dot Q is 0 or RC dot is 0, or they are parallel. Okay? That's the condition for a cross product to vanish. Right? Perhaps in what comes next, because I mean we'll do the following derivation, but perhaps I think what comes next is the third. It is the third scenario that's the most important. So imagine if Q and C coincide, in that case, of course, R dot Q equals RC, RQ dot equals RC dot, then the first term would vanish. So you would just get this conclusion, the time derivative of HAQ, right? Remember, this is the absolute moment of momentum relative to the point Q, okay, equals the torque, equals the external torque relative to Q, okay? And in the case where Q equals C, I was saying, Q, the moving point, is just the center of mass. In that case, it would be the absolute momentum, no, sorry, not the absolute moment, absolute moment of momentum relative to the center of mass equals, right, equals the torque of the external forces relative to the center of mass. So that's exactly what this 6DOF model will capture. So the thing is, the aerodynamic forces in general will create a torque relative to the center of gravity, which causes this spinning motion. Okay, so that's important ingredient which we will keep track of. Okay, and you also have a similar notion. Okay, before, remember, HAQ is called the absolute moment of momentum. What is the defining characteristic of that? Well, you use the absolute momentum, right? You use the absolute momentum, which is RJ dot with MJ dot with RJ. MJ, not dot. MJ times RJ dot. That's the linear momentum of particle MJ relative to the fixed coordinate system. So in the absolute momentum, the absolute moment of momentum is difficult to say. Okay, absolute moment of momentum, you use the absolute linear momentum, if that makes sense. In the absolute moment of momentum, the second argument in the cross product is the momentum relative to the lab frame, the fixed frame. So you can imagine, if we define a relative moment of momentum, the linear momentum would be changed to the relative momentum. So now, instead of using RJ dot, you use the time derivative of RJ minus RQ. So not only the arm is relative to Q, RJ minus RQ, this is the same, but in the momentum is now relative to the point Q. So this is called the relative moment of momentum. And you just do the same procedure. You just do the same procedure, take the time derivative using the definition of center of mass, etc., and you get this equation. So HRQ, that is the relative moment of momentum taking time derivative, okay, is still, you have this torque term, LEQ plus what? Plus RQ double dot, okay, plus RQ double dot cross m times RC minus RQ. So let's interpret what this means. This is the acceleration of Q, acceleration of vector of Q, cross with the linear momentum of a hypothetical particle whose mass is the total mass of the system. Actually, you know what? This does not have a nice interpretation. Okay, this does not have a nice interpretation. Anyway, so it's just this m. M times the position vector does not have a good physical interpretation. Okay, we'll give up on giving an interpretation for this, but basically, RQ double dot is the acceleration of Q. M is the total mass. RC minus RQ is the arm, or the relative position of the center of mass to Q. So once again, let's say, let's consider when does this term vanish. This term vanish. So this term vanish, once again, using the condition for vanishing of cross product. It can be R double Q dot Q equals 0, namely Q moves with constant velocity, or it can be RC equals RQ. So this is when Q is the center of the center of mass, right? Is the center of mass, or it can be the other scenario where you have the acceleration of Q parallel to the arm RC minus RQ. So comparing the two special cases, it is interesting to note that for both HAQ and HRQ, right, both the absolute moment of momentum and the relative moment of momentum, their time derivative equals the external torque when C equals R, when C equals Q. When C equals Q. So that is to say, if you change Q, if you substitute Q equals the center of mass, then it does not matter. Okay, and it does not matter if you put A or R in the superscript. It doesn't matter if it's a relative or absolute momentum. Its time derivative is just the external torque. Okay, actually, let me put that down here. So compare. We get we compare and we get H dot A C equals H RC dot. Okay, HAC dot equals HRC dot equals LE relative to C. Because this is what's going to be used the most in exterior ballistic application. We're interested in the torque about the center of mass. Okay, and it equals the derivative, the time derivative of the absolute moment of momentum and the relative moment of momentum. It does not make any difference here. So you can use the velocity relative to the center of mass here, or you can use the velocity relative to, well, the lap frame here. The equation of motion for both are the same. Or you can use the lap frame velocity here. It does not matter. Okay, so that's a nice little observation. Okay, and here we have more results. Kinetic energy. Yeah, for kinetic energy, the most important thing to note is that internal forces actually matter. So first of all, define kinetic energy as the sum of kinetic energy of all particles, the sum of half mj rj dot squared over j. Okay, and simply by using vector calculus identities, definition of center of mass, and all of that, you get this identity. So this is the identity that says T equals half big M RC dot squared plus the sum over J, half mj and then time derivative of Rj minus Rc quantity squared. So what does that say? The total kinetic energy of a system of particle equals the kinetic energy of a hypothetical particle whose mass is the total mass of the system, and its velocity, it's the velocity of the center of mass. So that's the first term. The first term is kinetic energy of a particle with total mass. It's a hypothetical. It's not a physical thing. Okay, it's a hypothetical particle whose total mass, whose mass is the total mass, and whose velocity is the same as the velocity of the center of mass. So that's the first term. Sometimes this is called the translational kinetic energy. Okay, and here you have also the kinetic energy of the system of particles moving relative to the center of mass. This is obvious because here the velocity is Rj minus Rc time derivative. So that's the relative velocity. And then square it gives you the relative speed squared. Summing over them gives you the kinetic energy of system of particles moving relative to the center of mass. All right, and now we have the celebrated work energy theorem, right? But for a system of particles. The work energy theorem of the system of particles essentially says this. It says for a system that the change in its kinetic energy, which is the left-hand side, equals the work done by the external forces during a time period, plus the work done by the internal forces. Okay, so this is, once again, this is a general statement. This is a general statement for system of particles. For system of particles, it is important to note that even though the equation of motion for, say, linear momentum and angular momentum requires no information of internal forces, internal forces do play a role when it comes to kinetic energy. And perhaps the most intuitive example would be an explosion. So a stationary bomb before and after explosion. The work is done purely due to explosive forces, which is purely internal. WE equals 0. WI is the change in the kinetic energy. There's that. So this is where we left off last time. And now let's try to consider some special results for a rigid body. Okay. So, okay. So we will start with considering rigid body. Okay. Here, let me pull out my notebook here. Okay, I'll write some new things. Okay. As we were saying, the principle of work and energy, or the work energy theorem, the principle, okay, sorry, this is ballistics, and right now we're still in the investigation of classical mechanics, ballistics, classical mechanics, rigid body. By the way, the fundamental equations for the dynamics of rigid body was dynamics as well as kinematics of rigid body was first discovered by Euler. And I think it was when Euler was in Prussia, was working in Prussia for Frederick the Great, and he was working with shipbuilding. It was during that period, and perhaps part of the effort for improving shipbuilding design, that he formulated the current theory on rigid body. So ballistic classical dynamics for rigid body. for rigid bodies. Okay, towards Euler's equation, which is perhaps one of the most fascinating system of linear, or not linear, but nonlinear ordinary differential equations. So Euler's equation is, as we shall see later on in the series, is a system of ODEs. Actually, we only have 15 minutes left, and I have to leave. So towards Euler's system of ODEs, which is nonlinear, and the study for that was also a great impetus in 19th century analysis. The study of, say, for example, elliptic functions was largely driven, not completely driven, but an important source of examples was rigid body motion. And the study of so-called integrable system in dynamical system was also largely driven by Euler's system of ODEs for rigid body. Okay. Anyway, a little piece of interesting math history in my opinion. So that's the principle last time where we left off is the principle of work and energy. It says delta Ke equals WE plus WI, right, for a system of particle. Obviously, because for a single particle, Wi would make no sense. There's no internal forces in a system in a single particle for a system of particle. Okay, so let's continue. If the particles remain at a constant distance apart, in the case of rigid bodies, then the internal forces do no work. So this is true for rigid body. The definition of rigid body is a system of particle among which the relative distance stays constant. Okay, for rigid body, so you have Rj minus Rk, length equals constant for all pairs Ij, Ik, Jk. Okay, so this is true for rigid body. This is just an idealized model. Okay, Wi is 0. Okay, that's the consequence. Okay, so yeah, and here's a little proof for that. So assume, or should say denote R1 and R2 be position of two particles whose distance apart remains constant. So you have R1, so we might have to finish this proof and call it a day. Okay, if I feel like doing more classical mechanics, I might do so in the near future because I just want to wrap things up, man. R1 and R2. So let R1 and R2 be positions of vectors. Position vectors of particles whose relative distance remain constant. Okay. With R1 minus R2 length always equal a constant. Okay, and now let's denote the force F and minus F to be the internal forces of one particle on the other, and also conversely. So internal forces F and minus F are as shown. So in this diagram here, let's assume this is F. So the force experienced by particle M1, let's call this M1, M2. So M1 experience force, internal force, okay, internal force of F, and M2 experience internal force is minus F. Okay, so the internal force is due to M2 alone. Let's say M2 exert a force of F on M1. So this is one pair. Okay, I'm not saying this is the only internal force of acting on M1. This is the only internal force. This is the only internal force M1 experiences due to M2. Does that make sense? Okay, so this guy M2 is pulling or pushing M1. And due to the third law of Newton, M2 experiences minus F from M1. Okay, hopefully this is clear. Okay, so, and now we wish to show WI is 0. So for this pair, we wish to show WI is 0. And once that's done, then it's totally clear for arbitrary pair, WI equals 0. Okay, so from this, let's call this 1. From 1, we have R1 minus R2 taking dot product with R1 minus R2 equals 0. Not 0, but constant. And now what we do? We want to take the time derivative on both sides, d over dt. So taking derivative d over dt, you can use the product rule. Right, that will be R1 minus R2 dot with the time derivative of R1 minus R2, and then plus the time derivative of R1 minus R2 dot with R1 minus R2. But because of symmetry in a dot product, it's just 2 R1 minus R2 dot with d over dt R1 minus R2 equals 0. It looks like a product rule, but it is very superficial. It's due to the symmetry of dot product. Okay, so there's that. Or you can write this as 2 R1 minus R2 dot with V1 minus V2 equals 0. Okay, so that's the result of constant distance, constant separation. So there's that. And let's calculate WI. Then WI, by definition, work. The total internal work would be the integral of F dot with V1 dt, and then plus the integral of minus F dot with V2 dt. This is a definition of force, a definition of work. Okay, this is WI. Okay, so you can easily collect the terms and get the integral of F dot with V1 minus V2. Right, V1 minus V2 dt. Okay. As we were saying from the picture, F is parallel to, in this picture, it's clear that F is parallel to R1 minus R2. Since F is parallel to R1 minus R2, you can write F as a multiple of R1 minus R2. You can write F equals alpha R1 minus R2 for some scalar alpha. For some scalar alpha, and the consequence of that would be WI equals the integral alpha R1 minus R2 dot with V1 minus V2. Of course, we established that that's 0. So now it is now rigorously proved. Due to the rigid body assumption, the internal work vanishes. So that finishes the proof. Okay. So the principle of work and energy for rigid body reduces to W delta KE equals the work done by external forces only. But in general, for a system of particle, internal forces do work. Okay. So there is that. I just wanted to finish writing some basic quantities related to rigid body. So for a rigid body, as we mentioned, we mean a system of particles such that the relative distances between pairs of points remain constant during its throughout its motion. Of course, this is an idealization. No such system exists actually, but for practical purposes, it's a good approximation. For example, the bullet prior to impact can be pretty much seen as a rigid body. Okay, during its flight, during its launch and flight, can pretty much seen as rigid body. So we can work with that. It's a good approximation. Moreover, the rigid body may not consist of a finite number of particles because usually we consider a continuum. Right? Usually, like a bullet is an extended body, so we can treat it as a continuum, not a finite collection of particles. Right? So we approximate that as a continuous distribution. Now, classically, this is a good idea, but of course we know, well, if you really want to zoom in, it is made out of atoms and molecules and stuff. We're not going to go over that. Okay, we're just going to treat the body as in a classical picture only. Sorry, quantum people. Okay, this is just a mass distribution, basically, a mass distribution that satisfies the rigid body assumption. Okay, so this is what we postulate. So basically, we postulate we can subdivide the body into a great many small parts. So we have applied our laws of motions for particles to this system. Basically, it allows us to do integrals. Okay, so basically that's the idea. We in our application of rigid body, although it is still possible to treat rigid body as a discrete collection, rigid body as a continuum. It is still very much possible, but for the rest of the analysis, we're going to treat rigid body as a continuum. Okay. Oh, thank you very much, Drago. I love when I see this guy stream. It motivates to study deeper, harder, and fall in love with the craft. Yeah. Thank you so much. This is so encouraging. That's the whole point, right? That's the whole point, because, I mean, I try not to be a lecturer, but rather a guy like try to read a text and engage with the text, right? And provide even criticisms and whatnot and supplements. So this is how I like to do things. But thank you very much for your encouragement. So I was saying, like, we're treating the rigid body as a continuum. So essentially you have a density distribution, rho xyz. What did we say? So in the kinetic energy, the total kinetic energy would be the integral. Okay. When we write integral, we actually mean a triple integral. I'm just going to be lazy and write one integral. Okay, the integral over the region R. So here you have a rigid body. It's a general shape. Okay, and it has a mass distribution inside it. Okay. Thank you so much. Always click on the video and click like, even don't have time for it right now. Guys, don't worry. I know these videos and lives are long, but think of this as my preparation session. This is what This is what behind the scene, okay, of how I publish my usual videos. So I usually have notes like this, and when I was doing the preparation, and then I turn this into a PowerPoint and record a more structured and concise video. Right, so I mean, you will see a more structured version, which is more concise. Like, don't worry if I'm not going to put everything in this long, torturous 4-hour stream, and then you have to study for a midterm, and then you have to click a 4-hour video. I'm not going to do that. Okay, so this is like my preparation, and everything done here will be put into more structured video. But this is just the preparation stage, and perhaps the point is to showcase that, like. Like this is, I mean, I'm not saying this is how you should study, but this is how I study. Okay, so yeah, T is the integral of half rho v squared, and then dv. Okay, let's just dv. This is imagine you have a little volume element here, okay, and the mass is rho dv. This is dm, okay, the dm. So, and it moves with the speed of v. It moves with the speed of v, so the kinetic energy for this dm, dke, is half mv dm squared, right? So that's the volume integral. Let's call this region R, stands for rigid. Integration over R, all right? And you have the center of mass. I'll just finish defining these quantities and I'll call it a day. So RC will investigate the equation of motion for rigid body later on. So that's the triple integral, the integral over R of the torque. Actually, I mean, you know what? Let's pick a position as the origin. Okay, that's the coordinate system, and here you have a position vector. The integral of rho R, which is a vector, by the way, RC is a vector, and then dV over the integral of rho dV. So basically that's the total mass here. Again, so you're going to write it as a 1 over big M, the integral of rho R dV. There you go. So that's RC. And then we need the total torque. So how do we define the total torque? Well, so you need the integral of the exterior forces. Right? Remember, only the exterior forces matter now, for all dynamical quantities is concerned. Because, as we said earlier, for the equations of motion, for both the linear and angular momentum, only external force and torques matter. Okay, and for rigid body in particular, internal forces don't matter either. In general, for a system of particle, WI do matter, but for rigid body, we just proved that it does not matter. So here, we just need to integrate we want to calculate the total force. Right? Yeah, we want to calculate the total force, FE dV. FE dV. So think of this as the force density. Think of a piece of the rigid body experience an external force. Right? You can think of external force as gravity. Okay, it experiences an external force. The little piece experiences a little the force density. So the force density is Fe. Okay, it's not a force, but rather force per volume. Okay, force density. And you integrate that over R. What do you get? The Newton's law of motion says, well, this is the total external force, right? This should be the center of mass, the d square, or should we say just R double dot, okay, RC double dot, RC double dot C times big M. Right, we derived that last time. Let me just check that real quick. Going back to July 25th here. Going back to July 25th, we got the law of yeah. So basically this one, right? The total force equals the time derivative of the total linear momentum. So what you can do is you can bring out d over dt. Actually, let me put it here. So so you can and also, okay, let me just use a different color. So recall RC is defined as 1 over m. Here, everything is finite, so finite summation, sum over j, mj rj. mj rj, all right? So here, the sum, the left-hand side, the sum, okay, you have dp over dt. Okay, sorry. dp over dt. The change in the rate of change of the total linear momentum is d over dt sum of mj vj. Okay, and what's that? Well, this is just because vj is also d over dt of rj, right? So you get d squared over dt, the sum of mj rj. But the sum of mj rj is exactly m times big M times rc. So that's just m times rc double dot. D squared over dt squared. So this is m rc double dot. So therefore, we reach the conclusion that m rc double dot equals the sum of total force. So you can think of this as follows. So imagine a hypothetical particle located at the center of mass of the system, and the mass is the total mass of the system. Okay, its law of motion or its equation of motion is given by the Newton's law for the single particle. So imagine all the external forces all act on that particle, all act the hypothetical RC particle with total mass m, and you just apply the regular Newton's law of motion to that particle. So that's exactly what we're trying to say here. The total external force now is an integral. It's the integral of the external force density equals the total mass times the acceleration of RC. Okay, so we have that, and what else? The total angular momentum. Okay, so the total angular momentum relative to O would be the integral of, so basically that's the integral of r cross v dm, dm times v. dm times v is the linear momentum, right? And then you just write dm as rho dv, so we get a volume integral. So it would be rho r, rho is a scalar, r cross v, and then dv. So that's the total angular momentum relative to O. Okay, and then what we have for the time derivative h dot, according to our last derivation here, 7/25 in the beginning, what is d over dh over dh over dt. dh over dt is the sum. dh over dt is here. We're just using one reference point. Okay, just one origin. There's no moving point and all of that. Okay, this is just one origin. So dh over dt, the time derivative of the total angular momentum, right here, is, the theorem says, is the sum of the total external torque. So let's do that. Let's just rewrite this as an integral form. Okay, so we have h dot equals LE. LE is the integral. Once again, you have R across FE dV. FE dV is the force, the infinitesimal force experienced by dm, and you just integrate over them. Okay, so that's it. So this is the relevant quantities we derived, but now in integral form. The laws, okay, the definition, this is the definition, okay, the definition, RC is the definition, and this is the law. This is the law. And this is the H definition of H, and this is the law. Okay, and later on we will continue discussing this. So now I have to go. Thank you guys very much for watching the stream, and we'll continue next time. We'll continue with maximum likelihood estimation, and we'll continue with rigid body dynamics, perhaps even sooner than next